Okay, everyone, hello. I'm moving into the camera frame. Hello, welcome to UCSC, our Silicon Valley program campus. I'm Sam, I'm somewhat the MC of the night, but I'm very happy that you're all here. Thank you very much. Obviously, a lot of students in the crowd are MSNLP students. Cheer. Thank you. But also, yeah, people from other schools and industry professionals in the area, which is very cool. Of course, we have some really exciting speakers tonight. First, we're going to be having Nathan Lambert, who is an expert on language model research and development. We'll also have Dylan Patel, who I think is yet to arrive, but will surely be here, an expert in the semiconductor and data center supply chain. And of course, Alessio Finelli, currently CTO at Decibel Partners over at Palo Alto, but also the co-host of the excellent Latent Space podcast, which is so near and dear to my heart. So the schedule for the night, real quick, is generally it's 3:30 p.m. until 6:30 p.m. tonight. And we're going to have speaker talks of about 45 minutes apiece, with like 15-minute breaks in between to get food and drinks and chat with people. So yeah, let's see, what else do we have? Of course, this is the NLP 280 seminar series, which is part of our MS NLP program. Every week we have people from around the area, academics and professionals, come in to talk to students about what they're working on and chat with students about all sorts of technical things. This was one instance of the program, but the guests are so good, we thought we would just open it up to the crowd, the public here. So thank you very much. Yeah, not much ado. I guess first speaker here, Nathan Lambert, of course, Senior Research Scientist at AI2, the Allen Institute for AI. As I mentioned before, he's an expert in language model post-training and alignment. And he's been a critical part of the Olmo family of models, the reward bench evaluation, as well as the Tulu series of papers, where they try to make sense of and establish best practices for all sorts of data mixing and post-training techniques. Previously, Nathan was a lead of the RLHF team at Hugging Face and got his PhD from UC Berkeley in RL-based robotic control, as far as I could tell. So yeah, Nate also, of course, has an excellent Interconnects blog and podcast, and co-hosts the Retort podcast, and has a habit of giving talks like this to universities all over the country. And he's here today to help us make sense of this new era of RL-trained language models and to give some perspective on recent events. So please give a round of applause for Nathan.
Okay, thanks for having me. I'm going to embarrass Sam a little bit because it's fun, but great example on just being kind and reaching out to people, engaging ways that you may be a fan of. I think it's hilarious that me and Alessio and Dylan are all coming, and I think that people often ask on how to get engagement from these people, and like I gotta give props. Like I was like, this is so random, but they're all going to be in one room, and that actually doesn't happen very frequently. So it's not an easy thing, and you did well. And I'm gonna yap about AI as we do. This is not the most technical talk. I think there's a technical period in it because when you don't know who exactly your audience is, that's definitely the safe direction to go. Many of you in this room will learn that the hard way when you just lose people by being too technical and really research-centric. But it's fun to kind of learn this. And this is my broad intro. Everyone is hearing about reinforcement learning these days, and I've already double-clicked. I wanted to start on kind of what would be called a boomer reference paper. I think T.D. Gammon, it's either 1992 or 95, I think it might have been pre-printed in 92, was a paper, it's Tesoro et al., and really not a ton has changed in DeepRL since then. I think this is a paper from 1992 where they use self-play to get superhuman performance on a game. They use neural networks to learn value functions. And it's just amazing how that idea is not new, but a lot of progress. So this was on backgammon. I think some people here have probably played this, but not a lot is new. And then you go for a long time, and there's a whole deep learning revolution, and these things at the core of reinforced learning are still often the same. And today we're talking about things like RLHF, this reinforcement learning from human feedback, which has turned into now just talking about just reinforcement learning generally. And kind of contextualizing this transition from ChatGPT, which was about RLHF, to what we were talking about now, which is just this RL training for reasoning on verifiable outcomes. It's like, how did RLHF actually become a thing? There's a 2018 paper here, which is kind of proposing the idea of reward models as something that can capture complex human values and can be used to study in a large suite of different machine learning systems, and this quickly got applied to NLP. The kind of canonical RLHF reference, the Cristiano et al., is actually for control of simulated robotic agents. This is a really great paper to kind of understand what some of these seminal figures were thinking about, and it's like how we can capture such complex signals as comparing two things that might be hard to really generate a good answer on, and then have machine learning systems kind of incrementally improve their performance on a variety of tasks from this. It really quickly evolved, and then from the actual ChatGPT announcement, we can read this benign quote that's like, we trained this model using reinforcement learning from human feedback with the same methods as InstructGPT with different, some subtle changes that they don't tell us. And really, RLHF was necessary to go through this door of ChatGPT style models that we're all used to using today. It really wasn't sufficient, and it wasn't the leading thing that people were thinking about when they're talking about language models in the last few years. It was really just a cherry on top. And now we kind of have this bigger RL phase where this is a great meme to kind of get us older RL researchers interested. Is like, RLHF was this really necessary thing and very important, and then how did it come to be that RL actually becomes even more important to this AI ecosystem again? So when RLHF came out, I think the community spent a year plus really figuring out how to implement good open source tooling that works on language models with RL. I would say that ChatGPT came out end of 2022, and pretty much all of 2023, and to this day, there are very few models that are actually trained with RL for this preference learning problem that was originally introduced for. So most of this time, RLHF was building this really nice RL infrastructure for language models that made this explosion of research that we're seeing today. I don't talk about a ton of these blog posts and papers that are coming on RL training and different subtleties to doing that for reasoning. But without RLHF, this takeoff that we're seeing in an academic sense would really never have happened. And a lot of this story is also just the kind of funny way that things happen in machine learning. Training on verifiable outcomes like this O1 and DeepSeek R1 was really not new to the field of AI. Here's a series of papers from 2022 to 2024 with some type of reasoning training that requires checking the answer for the work. There's things like self-taught reasoner, Vine PPO, training RL with code execution feedback. All of these ideas were in the academic literature before O1 was released, before DeepSeek R1 was released. So it's just the way things happen is that timing is really important, and things can change really fast when there's so much investment in the area. And then this kind of O1 blog post, September 12th, was when it's a paradigm shift in how people see the validity and value of different methods, even though not a lot had changed in the literature, but these new language models trained with RL to perform complex reasoning, paraphrasing what OpenAI said, have changed quite a lot. You can visualize this in different ways. This is from when O3 was released, and Bradley Goodside plotted the ARC AGI scores for various OpenAI models and put them over time. And this is what it looks like when a paradigm shift happens. And we solve an evaluation overnight and just need to rethink kind of what is the challenge that the cutting edge of the field is going to be looking at. So I'm going to take the technical portion of this talk and kind of talk about like, what is this RL training? How do you think about reinforcement learning on language models relative to the classical definitions of RL? Shout out to Sutton and Bartow for winning the Turing Award. Could have put a slide in there for them, but I didn't. And I think if you're looking to learn this, that's still the place to start. They have a great textbook that's on my desk. And before doing this, I'm going to kind of explain more of post-training. And one of the takeaways for this talk is kind of a lot of post-training is no longer in vogue, RLHF, and all people are talking about reinforcement learning for reasoning. These models like DeepSeek and O1 are doing all of these techniques in a complicated pipeline. The reasoning stuff is the new hot thing, but you really, if you want to train a leading frontier model, you need to do all of this still. So that's kind of how complex technologies are pushed forward. You keep building on what has come before. So there's many different words that you can describe post-training with. Allen Institute, we use language model adaptation, which is really going to say that we have a really strong pre-trained language model on large amounts of web text, and it's not really set to do any one specific task. It's going to be a fancy autocomplete. In reality, now these base models are exposed to instructions and other things, and you can really use them in a lot more interesting ways than GPT-2 era base models, which were very sensitive. And what you do is you take these and you come up with a list of tasks that you want the models to be good at. You want to be able to answer questions. You want to have them be useful at writing really useful code and solving math problems. And you kind of identify this, and then post-training is the art and science of actually pulling this out of the language model and getting them to be really useful in specific things. Back in the era of InstructGPT and ChatGPT, this was a quite simple process where you kind of had your base model, you did some supervised fine-tuning or instruction tuning on some human-written instructions and answers. It was really human-heavy at the time. And then you would train a reward model and do reinforced learning from human feedback. Kind of this really forward pass and a lot of human data. And it worked. It got us to ChatGPT. But yeah, this is mostly what I said. It was kind of seen as a three-stage process. You look at the InstructGPT paper. You look at a lot of early blog posts and things on RLHF. You'll see people just say it's a three-stage process a lot. And that's definitely fairly outdated. It was a three-stage process. And now it is a much more complex process where you're addressing more capabilities in your data. The evaluations that people are saying when they release a model are only a subset of the things that they actually care about, both for their users and internal applications. And the shift from using human completions to synthetic data is extreme. So the language models are much better at answering almost any code or math problem than the annotator that you can hire. And the annotators are really being pushed out into the fringes of trying to get new data for really niche capabilities and things that the models don't know how to do today. But this gives us kind of a very different pipeline. You can see this is the figure that, for people that were chatting earlier, I referenced the llama figure. And you get a lot of, if people like, if ChatGPT had one of these system diagrams for post-training, it would definitely be far more complicated. And it's just, it's a many-staged process with lots of data sources and kind of this human evaluation that can be also used as training data with multiple loss functions. So saying that you're just doing post-training, it requires a lot of like, okay, how are you actually doing this? What are you prioritizing? You have a lot of tools you could use. What are the ones that you're going to focus on? And kind of you can visualize this if we use my same block diagrams. There's kind of more feedback loops, there's more steps, and there's kind of this idea of an intermediate stage where you'll just kind of keep training your N+1 model and keep making it a little bit better with different loss functions, different data, and so on. And you can see some model references if you want to find various papers on explaining these processes that were used. And I like to summarize this as now we kind of have three tools in our kit for post-training as different loss functions and different types of data. We have supervised fine-tuning, also known as instruction fine-tuning. This is where you have a prompt and a completion, and we're using this auto-regressive loss function to get the model to predict those tokens more accurately. And this is really good for teaching format and kind of the base of following question answering abilities. And kind of this teaching formatting and thinking about what this auto-regressive loss function would be doing is really good as we contrast these next stages, because the optimization techniques get more open-ended and more flexible for the model to kind of fill in what it actually should be learning from the data or signal that you're showing it and the loss function that you're using. So then we kind of have these preference fine-tuning and reinforcement fine-tuning. Preference fine-tuning is a generalization of this reinforced learning from human feedback. You have this pairwise data and you use a contrastive loss function, which can either be something like DPO or some RL function that's prioritizing a reward model, which is just very different than predicting the next token in the sequence. And this is a very rich area. I think preference fine-tuning has very much been associated with like a narrow layer of style, but a lot of recent papers show that you can meaningfully improve performance on math and other things with this type of loss function. So I would expect that, and I'm like invested in this kind of idea of RLHF continuing to be pushed in the research field and in kind of industrial practice. And a lot of people kind of underestimate it for the time being. But that's not to say this final one, what brings people here, the reinforcement fine-tuning, is also like, it's credible that this is a moment of focus, because in many ways it is so easy to boost performance on tasks that people care about with this reinforcement fine-tuning. And I'll explain what this is in more detail in RL technically in just a couple slides. But really just to double down on this point, what reinforcement fine-tuning and these kind of new methods are doing is, I talked about pipelines becoming more complicated, and DeepSeek R1 and OpenAI O1, and especially if we look at things like what has been rumored with GPT-5, where they're like, it's just going to be one system. Like, there's a really big reconfiguration of how many steps and how complicated it is to train one of these models, especially in these reasoning and post-training stages. And RL is taking a much bigger amount of the attention in compute, in acquiring new data, in interpreting the importance of the results. Okay, so now the technical portion starts. We're going to look at reinforced learning basics. I hope many people have seen some sort of diagram like this before. Reinforcement learning is really motivated by some notion of trial and error learning or sequential decision making in uncertainty. Both of those framings, when you think about using a chat model or a reasoning model like O1 or even ChatGPT, are like, okay, how does trial and error learning or sequential decision making get folded into these kind of basic question and answer tasks that you're doing? And we'll break this down, but really these notions of an agent that takes an action in an environment and the environment gives a reward have been very contorted with language models to be a kind of weird corner case of the potential setup. So if you at least think about this in language before we get to the actual way training is done, the agent is a language model, and when you ask the question to the language model, that question is the state that we are modeling, and the answer that the language model gives is an action. And the target environment doesn't really exist. I think most of this training that we're doing, we're not modeling the human. They don't have, they probably experiment with things where language models are talking to each other to try to enable multiple tasks. But for most part, it's just a question and then an answer. There's no environment other than a potential reward model or something to check if an answer was correct. So if you take that, what I'm saying is it's like not really that much of an iterative process in terms of multi-turn questions or anything like this. You pull a prompt out of your training data, you get a completion from a language model, and then RLHF is you grade the completion with a reward model, which is trained on that pairwise preference data, and then it gives a reward that you can then update the agent on. You do all this in normal machine learning things where you have batches of data and it takes a while to train it, but to simplify it, this is what standard RLHF would look like. If we're to expand this in the technical level, I think there's a lot of the most common word you would hear for the last few years is PPO, which is proximal policy optimization. What this is just some RL algorithm, and if you actually want to implement this with language models, you need to have multiple copies of language models. So you have a policy model, which is what actually is generating the text you would read. You have a reference model to help constrain the optimization so that you don't end up just generating gibberish, and then you sometimes have a value model. I think if you were to hear about GRPO, so DeepSeek's group robust or group R policy optimization, GRPO, they essentially have a different way of approximating value that doesn't actually need a learned model. So you just look at the answers relative to your batch and if they're right. But this is kind of a standard reinforced learning setup if you're going to do this with language models in any task. You have to have a bunch of copies of the model, and then in RLHF it goes to a reward model as well. And then if we were to think about transitioning from this RLHF era of language models to something where we're looking on a verifiable answer, the simple idea for a researcher is, okay, like let's add a ground truth reward to the model. Let's give the model an extra bonus on top of the reward model if the answer is actually right. And this is what what we first tried when we were training our Tulu models. And really what it turns out is the thing that is used for DeepSeek is what we do at AI2 is like you don't actually need reward models for all these math and code problems. And you just take a prompt, you generate an answer, and you have some checker to see if the answer was right. And then you do this RL loop, and that simple thing of language model answers a question, check if the answer was right, update based on long literature of reinforcement learning policy updates. The models get better at a ton of things, and there's not a lot of downsides. In terms of starting to implement this on our models, it's very much like, oh, that wasn't so hard. It just kind of works. That wasn't a whole couple months of rabbit hole. It just we just kind of tweaked our RLHF recipe, and it was potentially easier. So if we kind of zoom out, what we call reinforcement learning with verifiable rewards is this loop, where you have a language model, you still have the reference models, so there's still some stuff buried in here, but it's really just checking if the answers are right, and then updating with this reinforcement learning loss function that has been around for a long time. So this is something that is really nice because it is so simple, and at the same time, this sort of talk kind of, I don't know how things like DeepSeek exactly are trained because all the details on data and making the infrastructure really good are really complicated. So it takes a lot of engineering effort to have all that data, to know how to put it together, and there's things that you can draw on from past RL literature, and it is the thing that is complicated now, and I'll cut myself off before I say emerging research things that are TBD and if they're actually right. And the core of these things is the data, and OpenAI released this reinforcement fine-tuning API, or they didn't release, they announced an API in the fall, and they gave this example on data, which is like a biology example, which is unnecessarily confusing when you can do a math example. But really you have a prompt and an answer. And an example would be like this math problems. Could be in our training data for our next models, such as like a big, like what is this multiplication thing, something that we could all do but don't want to, and you have an answer. And this is the type of thing that you can train a base model on, and it'll like learn to have chain of thought. And it's pretty wild, but like that's all you need to give a base model. And you need to have some distribution of it, but it learns to do intermediate steps. The answers it generates are much longer, and we're gonna dig as a community into this and like what actual data you need to extract all these capabilities, but there's a lot of open fields by which we can explore. Some examples you can find in our Hugging Face. There's also clever things like more textual domains where you can say, write me a poem about a goldfish, and then you can add a constraint that start every sentence with the letter G. And that is something that is also verifiable. It's less obvious than math, but still very intuitive. And the sort of thing that people are going to keep pushing these training techniques into to kind of create things that are like, adding constraints like this on text is really useful for people using models. You like want the model to respond in a really specific way. So it's not just math and code, but math and code is the obvious hill to climb on. OpenAI referred to this as the blog post as grading functions. I have an example on the right, which is like what the code is handling here when you're doing ancillary extraction is all the various ways you can express the same answer. I expressed 5 different ways that you could express the same number there, and language models effectively get tuned down to their own their own common language. But the important thing to think about from this slide is what happens when you're doing math and code and precise instruction following all at the same time. You need some rubric or way of reward shaping these different inputs to the model at the same time, so we can learn everything at once. And that's kind of a classic deep learning problem, which is like you need to make sure the model is learning everything. When it was just tokens, when you're predicting the next token, that's pretty easy. But in this RL sense, where it's going to be, we need to balance the amount of problems in our batches so that as we do this long training curriculum, they all kind of finish learning at the same time. There's definitely flexibility in that, but there's a lot of there's going to be art in understanding how we should shape these rewards and how we should shape the data set for when we're training unverifiable outputs. If you've done RL training before, you've seen a lot of curves that are supposed to start, and there's a time x-axis and a score y-axis, and it's supposed to be that it goes up, it does its little arc. And really, when you're doing language models with this verifiable rewards, it looks a lot like this. The 3 plots here are KL, which is the KL distance, which is essentially how much the model changes relative to the base policy, and then 2 representations of reward. The middle one includes the KL penalty, is the only difference. So the last 2 are really similar. And what this plot is showing is a variation on how big the KL penalty is, but the real takeaway is like this looks like very normal RL training when you do it. And if you've been playing around, especially in RLHF and other post-training before this, it's like, it's a lot of it looks very simple, which is a lot of why I'm optimistic about it continuing to get better. So this is a basic like hyperparameter sweep type thing, but we've also found in practice you can do funky things and keep getting performance. So it's these three curves, three colors are three different RL runs where we kind of took what you can think of as like an instruction model, an SFD model, and then we did RL 3 times, and we just wanted the numbers to keep going up, and they were. So we like did RL, and then you reset it, and then you do RL again, and reset it, and do RL, and do it, reset it. So this is kind of like saying the funky things that I was saying, where you can just get most of the way there by just thinking if you do like one thing and one other thing. But when you start to just embrace kind of a bit of chaos and controlled chaos with maybe changing the data, you can keep getting more performance out of these methods in kind of not intuitive ways. So this was for our OLMO2 instruct model, either 7 or 13B. That's 13B, it says on the bottom. So there's a paper for that. If you can't find it, please reach out. But it explains this plot in a bit more detail. Another example is for our kind of general post-training recipes for this like 2-3 8B model. All we did was switch from this PPO algorithm to the GRPO algorithm, and we got like a very meaningful eval shift using the same data set, the same starting point, and it's just like, it's hard to express. Like, for context, the original Tulu project was about 4-month project with like 20 people, and this sort of 1-point gain is a very major delta in the like relative impact of your project. So for us to just change the RL algorithm and not change anything else about our pipeline and get this level of improvement is a very big deal in research. This is the type of thing that's like an easy change that makes it the difference between anyone caring about your model and not. So at the cutting edge, to have that type of performance improvement is really an optimistic signal. And it's the sort of thing where I'm like, there's so much low-hanging fruit in training these models. It's if you just incrementally try things from informed priors, you're normally going to find improvements in your evals. And I don't know if there are people, it's an NLP master's program. I don't know if there are RL people in like deep RL background in the audience, but one of the most common critiques when we get when presenting this kind of language model RL work around is that this is not new, and it is just like classic RL, which is just give the agent a reward, a sparse reward when it does something right. And it is. I think the innovation here is kind of stability of implementation and making it really easy to do without degradation outside of domains. So when we train on math and code, it's not like the model gets worse at general chat abilities or anything like this. Even sometimes it like fixes the model and makes them a little bit better. So there's a lot of weird stuff with this RL loss function, but it just being so easy to apply and stable, largely from this major open source infrastructure work from RLHF to kind of get all the bugs out of the way, is why there's so many papers on this right now. And there's a lot of questions relating these two things. So I've talked a lot about RL training, and I also motivated this by O1 and inference time scaling. And this is the plot that OpenAI released that collectively nerd sniped the entire AI field, where they showed this kind of training time compute and test time compute. And largely, the point is that RL training and test time compute are really complementary things, and you can kind of see a complex relationship forming between them. And really, this reinforcement learning training can improve scores dramatically without touching the inference time compute that we're showing here. So in all the results that we talked about for our post-training recipes with Tulu, the sequence length going up is not really something that we've done publicly right now. But at the same time, when you look at DeepSeek R1, it is the same loss function, and the sequence length is an important marker of some pieces of the RL training. And really how I phrase this is that the RL training is the most popular way of doing inference time compute right now, but in a lot of ways it's natural to expand that. I think I learned a lot from Dylan on like how brutally expensive long context inference is. And if you're going to do something like best of n, you can actually scale your inference much better because you don't need to do as many long context inferences. So this is something that I'm trying to form more opinions about, but I look at things like O1 Pro and stuff like that. And I'm really optimistic about not just this RL training for inference time compute. So yeah, so this is kind of a summary of the same slide with less details, where it's like there's just more science that people are talking about this parallel inference time compute region in addition to the RL training. The one that if you want to read more about, I think the Claude 3.7 blog post was really nice on kind of talking about why they're exploring it and why they didn't include it right now. So I'm going to kind of go through some of the recent models. I've been writing a lot of blog posts on this and just kind of share my worldview and how I kind of process releases and how I think that a lot of people in the audience could benefit from it. I think as a researcher, my prior is trying to understand where the field is going. And I use the models, but if you're an academic or student, like your business bottom line is not about whether or not you need to use the right model at this instant. It's more of like, how should I make decisions on where AI is going to be in a few years, and how do you make bets based on that forecasting? So the one that kind of reignited a lot of interest in AI broadly and RL specifically was DeepSeek R1. And really this is about having the recipe for people to build on in terms of training these reasoning models and to have the actual weights to do things like distillation. Distillation is where most of the work will be, which is when you take the DeepSeek R1 model, you generate completions from it, and you do some limited post-training on a smaller model. And a lot of people will do this, but their long-term, more like accelerationary effect is that everybody is really confident that you can do this 4-step pipeline with large-scale RL and make a model like this. And they have a lot of cost numbers on DeepSeek V3. Those are complementary to what's seen here. It's like with an efficient team, you can train models pretty effectively, very effectively. And that really confirmed a lot of the rumors about OpenAI O1. And people have said this a lot, which is like the yin to DeepSeek's yang or whatever is Grok 3, which is like having a lot of compute really still matters. And Grok was founded like 19 or 20 months ago, XAI was, and they have a state-of-the-art model. I honestly feel like I under-index on it, mostly because it's a new interface. They have to go to the model and form new habits. I think the lesson is to be very open-minded and try to use AI tools that you are not as used to using, and to actually actively go out of your way to try some of these new models that people are talking about. It is a cost in time, but it really helps you extract the potential productivity from the best models. And a lot of the Grok release was around this idea that Grok was supposed to be based and things. It turned out that in practice it wasn't as based as they were advertising, but it expanded the window by which people would think that model personalities could exist. And it kind of, they really are in the conversation with OpenAI, Anthropic, and Google. And there could be more companies that do this. I think there's a lot of other companies out there that have very substantial funding and very substantial kind of talent pedigree. And AI is not, it's not defined who will have the best models and who will have the experience that people like, even though there kind of have been key players for multiple years. It's very exciting in this way that a new player can kind of just join what is happening. And when there are more people and kind of the race is expanding in that way, it's kind of going to make everything go faster because there's more competition before a kind of potential slowdown and consolidation when all the economic things kick in and risk becomes more real. Also that this model, and we'll see this when I talk about Claude on the next slide, search and optional reasoning or reasoning of some form are becoming an industry standard. I think one of my most common use cases of ChatGPT particularly is search. I think they're doing a very good job, and trying to compare how the different models use that is very worthwhile. With XAI's release, kind of opened another evaluation rabbit hole for models. XAI did not release a ton of official numbers. These are the official numbers on the left from the live stream, which are on reasoning benchmarks. The text is really small. You don't really need to see the scores. When Grok was released and publicly available, it was the top performing model. The asterisk is that it's top performing based on some added inference time compute. All of these models are doing inference time compute in a different way. The OpenAI blog post kind of famously had some shading And there's something like they do majority voting at 64 samples. There's also the confounding factor of we don't know like how many tokens they spend on thinking relative to their answer. So all of these inference time compute announcements are going to get far messier before they start getting cleaner, because with RL you can really scale the amount of tokens it spends on an answer, and you can also do things like parallel test time with majority voting, what is going to turn into kind of bespoke verifiers for each model. So I think that's like likely where O1 Pro type things are going, and comparing that is extremely hard. I think it's really quickly going to not be an apples to apples comparison, and one of those things where you need to figure out your own use cases and kind of talk to a lot of people that are using these models. Then Claude joins this conversation. The thing that, in many ways, this Claude user interface is closer to what Grok has been doing, where they have a button that you need to click to get more thinking power. DeepSeek's is also like this. It's just that the DeepSeek R1 model itself was so popular, but in the app, if you use DeepSeek, there's a thinking button that does the same thing. I actually have been thinking and writing a lot that I think having to select thinking manually is a very bad user experience, because people are figuring out what they use AI for, and it's not really clear if you don't know what you're using something for when you should have the model try harder on the task. It's a very abstract notion. At the same time, Claude is going to get search. So it's like these are the user interfaces that we have, which is you can spend more on compute and you can get outside information. And that's like, it feels like this kind of imperfect thing that we're going to move through, and it's really like, how does all of this get synergized into one model? In some ways, this is kind of related to this just being a rapid hill climb on the generation of models that we have. Dario Amodei, CEO of Anthropic, said that like most of the progress has been through post-training in recent years, or in recent months, and he was talking about this Claude 3.7 model, and this kind of leads into what we're talking about last, which is going to be the GPT 4.5. So there's a GPT 4.5 was kind of received in an odd way. I think watching the live stream and reading Sam Altman's tweets around it are really, really weird, because they're trying to make it a low-key thing while simultaneously being the biggest model that they've released. We don't have exact details, but approximately an order of magnitude more compute than the GPT-4 model. It's a good exercise to look at the costs for various new architectures of OpenAI when they are released relative to the peer model at the time. So the GPT 4.5 model, when it was released, I think the API pricing, if the API might not be available yet, is like $150 per million output tokens, $15 or $30 per million input, and GPT 4.0 is like 30 times cheaper right now. But at the launch of GPT-4, it was something like the most expensive version with the longest context. It was like $30 per input million and $120 per output million. So the prices that we're seeing now are not extraordinary relative to where they were just 2 years ago for the newest architectures, and they just keep getting driven down, down, and down. And that's the sort of thing that people fix on is price, and that's mostly because OpenAI was just talking about like EQ and this personality and reduced hallucinations, which are really hard for users to pick up on. The emotional depth thing that people have been doing is finishing green texts, which I've done a lot of these, and they're very funny. There's weird things where it feels like the model is referencing your past chats to know about people that aren't public figures, because the date cutoff was supposedly still in 2023 for these models. So it's not really clear exactly what OpenAI is doing in ChatGPT with that regards, but these have been good. It's like you don't have to cherry pick them. Like the model does do a good job at this task. And mostly why I'm excited about this is that base models really unlock a lot more in post-training. If we're thinking about the Claude release, where the CEO is like most of these improvements are from post-training, it's like they really haven't needed to move up this level, but a lot of recent progress kind of shows that you can pull capabilities out of with post-training. We talk about doing really basic math problems with RL, and you get this chain of thought and this kind of generalization to more mathematical reasoning tasks. So I would say that we kind of need the infrastructure to train and use this GPT 4.5 model fully, but everything in the industry points that this is the direction that it is going. To use these bigger models, I mean, XAI, we don't know how big Grok is. It was probably previously the biggest model being served to users. And Claude and Anthropic have insinuated that Claude 4 is going to be well larger as well. So there's kind of this debate where we go from NeurIPS and is this the end of scaling as we know it to bigger models are still very impressive. And I would say the evidence will probably hopefully back me up that these bigger base models provide richer platforms where post-training can extract more performance from them over time. But you need very sophisticated infrastructure to actually do this on a model of GPT 4.5 scale. So this is probably the best plot in terms of performance for GPT 4.5 relative to 4.0. The lower circle is 4.0 on GPQA, and the upper is GPT 4.5, where all the other models on this plot are reasoning models. The reasoning models are benefited a lot on GPQA, which is kind of like a really complex STEM question answering domain. So if you ignore the reasoning models, the same type of training, which is just a general chat instruct model, scaling up has given dramatic improvements on kind of what is seen as one of the core benchmarks in the field. So if reasoning had not happened, this would be probably the biggest step in evaluation scores that we have seen in months. So like the reasoning explosion has desensitized a lot of us to major steps in some of the evaluations that we care about, which is probably more fun and exciting, but it's fun context. And related to this big model, there's a quote from the DeepSeek paper. It's small. They said, while distillation strategies are both economical and effective, advancing beyond the boundaries of intelligence may still require more powerful base models and larger scale reinforcement learning. So this is one of my pieces of support for understanding that it's much easier to pull performance out of a strong base model than it is to, with kind of instruction fine-tuning, teach them to solve really complicated tasks. Because this instruction fine-tuning is one token at a time, it kind of makes sense that this complexity would be much more handled much better with these kind of more general loss functions where the model can kind of learn and explore in its own way. Okay, so I'm almost done. This is kind of the provocative part of the talk, which is like, what does it mean for RL to be the focal point of language modeling development? And it's like we've talked about this a lot with the acceleration of performance on key benchmarks, but like, how does this expand to generalization? And like, if pre-training is much slower, like, what types of data can we pull in? So some of us have talked about this before the talk, but OpenAI is saying that they're pretty much throwing RL at every one of their important public avenues, from deep research being trained with RL for some internet browsing task to their Kua operator model, which is a GPT 4.0 model being trained to navigate the web with RL. We don't know the specifics, but it pops up a lot. And one of the ways that I draw this in is with the bitter lesson, where Rich Sun essentially had this essay that really highlighted the fact that most research ideas that win out in time are those that can be scaled simply and don't have unnecessary kind of human priors in them. And the methods that he highlights in this essay are those that kind of combine search and learning. If we look back at deep learning, it's a pretty obvious analogy that deep learning has been immensely successful at kind of just scaling and processing lots of raw information. And this new reinforcement learning training is, the model is trying multiple completions to a certain prompt and getting really sparse feedback on this. So it is a form of search during training that is very general and hopefully can continue to be scaled. So this essay is, if you haven't read it, is 100% worth reading. He also has an essay on verification, which is very complementary, especially as we talk about whether or not these reasoning models will generalize. So this is when you change the theme on a slide to change the footer, all the text boxes get resized. So I normally miss one. But this is a pointer to the fact that Rich has another essay on verification, which is also very old, and it's just the kind of thing of, he has been consistently right on a lot of these ideas and what can unlock continued performance in machine learning systems. And there's a lot of analogies to what's happening now, where we have media covering research blog posts from many universities as major technological breakthroughs. It feels a lot like the alpaca moment, But kind of because what I talked about with infrastructure existing in the way that it is, it's going to be a kind of much more tangible and sustained version of progress relative to when these first chat models were coming out, which were just kind of limited fine-tunes on some human data to kind of mimic ChatGPT. And then, oh, I lost that screen, that's fine. So it generally went back to this. We said that RLHF was necessary but not sufficient, but this kind of RL could be where all the labs are investing all their resources as they continue to try to improve the performance of the models in really meaningful tasks. And the kind of thought experiment is like, what if this kind of post-training idea? So right now we're stuck with pre-training and post-training. And what if post-training can be just training, where we have a kind of gym of countless tasks from robotics to math to code to biology, where the models are trying some sort of action in the world and getting feedback on what is happening, and continue to be trained in the domains that we care about. This is obviously a existentially expensive and hard question for AI, but it kind of opens the door to we're actually training on tasks that we care about. If we can verify them, we have a format where the language models can take feedback on these types of actual specific questions rather than just general text. So to the extent that this ambition can be true, it would be very fun to kind of keep driving meaningful tasks, but I would not bet on this actually being successful. It would just benefit me if that was the case. And this is like kind of at the sort of rough ballpark, which is, if you look at the DeepSeek V3 paper, it's like well less than 1% of the compute in GPU hours was on post-training. And there was a tweet that is now deleted where a member of the team said that DeepSeek R1 took a few weeks to train, which is this large-scale reinforcement learning. So even if you just take this few weeks on the same cluster, it would already be such a huge increase in compute. I think this is obviously not a comparison that you can use in any sort of meaningful argument, but it is directionally where the field is going. And if you kind of keep thinking about this, and if there is just one internet to train on, it is a fun proposition to kind of keep scaling where we're going and kind of see the limits of it. So these insights and the few actual technical results I shared are built on a large team at AI2, and a lot of them are pictured here. But thanks for having me. It should be a fun time to be an RL or an AI researcher, and hopefully it's a little bit easier to make sense of what is going on.
Thank you, Nate, very much. We have, I think, maybe 10 to 15 minutes for questions, and then we'll be taking a short 10-minute break between speakers to get Dylan set up and going on the camera, on the computer. So if anyone has any questions, I'll throw a mic to you. Start with Cal, and I'll move the mic around.
Yeah, so during your methodology kind of slide, and you were talking about what you do to stay on top of things, do you have any like sources of information you're constantly looking at? Is it just conferences, or are you kind of doing a large scale search of the internet when you do these things?
I think that I'm in a lucky position where it's mostly pruned. So it's a mix of a Twitter feed, but I don't have to be too scrolling for too long. And then my paid subscribers have access to a Discord. It's not saying that you have to pay. It's like if you can't afford it, it'll give you access. But it's generally a community that is willing to like try to curate a high effort community, and people share and discuss things there. And then also like having a job where people are trying to stay at the frontier of AI and they discuss these things. So I would say I get a roughly uniform amount of news there, but most of the news you largely ignore. So I definitely read fewer papers than people expect, and all of this, and it's like there's a very narrow number of people you actually have to listen to and be able to like understand what they are actually saying.
Cool, and just to follow up on that, do you have any recommendations for us as students or kind of younger researchers trying to find this information?
There are things like I have a list of Substack recommendations on my blog, which are things that I at least read sometimes and think are good. There's that path. And then it's just like being curious. I think that it's not necessarily the case that everyone that is a student should be trying to keep up. I think most students should actually not be trying to keep up with everything, because like that is not, like your cutting edge is to learn skills that are useful for building things, and then it is a certain number of businesses that you actually have to make like game time decisions on what is happening. So there's kind of balance of it's fun, but you don't actually have to. But normally I err on the side of students are trying to plug in more than is beneficial.
Cool. Thank you.
I'll walk over to the back and then I'll get in the front here. As I'm walking over, totally unqualified opinion, but there's a guy on Twitter named Swyx, S-W-Y-X, and he has a high signal AI list on Twitter that can get you started if you want to burn your time on that.
He also has a good newsletter.
It's
The daily newsletter is good.
Too, I think.
Yeah.
Thanks for your talk. Two quick questions for you. Hopefully this is not overly technical. One of the things I was wondering, I think you'd be probably well qualified to kind of talk about this, but I was really wondering, in classical RL, there's kind of this problem of reward attribution. How much does pre-training actually kind of address this problem in like language model RL, especially with huge chains of thought with reasoning?
Honestly, I feel like I should have you can come ask me this after as well. I don't have a good answer. I think it's mostly that the language itself, when it's organized, just does a lot that makes it flexible to be used in a lot of these domains. I think we're leaning on the representation of language, and when you think about reward attribution in the RL sense, it's much more complicated with this multi-turn sequential thing that we're not really doing. So I think for an agent that's taking probabilistic actions and then it takes 100 actions to get to one very sparse reward, I think attribution is a much more interesting problem here, but we're kind of jerry-rigging language to guide us to one really specific thing, where especially when it's autoregressive, it's I think it's still somewhat segmented, but it may become more overlapping.
I promised Darian I'm going to come up to you, but first, thank you.
Oh, thanks. Actually, I have a quick question. I see you mentioned about AI infrastructure and inference for that. What do you think currently the AI infrastructure lack of for the training and inference, aside from the ability to process larger and larger models?
Can I just make you wait until Dylan talks? I mean, it's different. It's just different ways that the infrastructure is tested based on the training regime. So I think it's they all have this trade-off of memory, flops, and one other thing. There's the three things that Dylan always mentions. But what is happening is long context uses a lot more memory. And for example, there's GPUs that have more memory, but they have fewer flops per memory. So it's you can fit a bigger model in, but you train slower. And then the third thing is communication speed. And then essentially you have a co-design on your cluster between how big of a model and how fast you can train it, which is based on, and the architecture is based on the communication protocol you need to have between nodes. So they all work together to end up you're trying to do experiments faster or train bigger models or more specific models, but it's you can't push a specific direction without improving the infrastructure.
That's very insightful. Thank you.
Darian, as promised, and then I'll get Jeff afterwards. So.
I was just curious. Well, thank you very much for the talk, first of all. But I know that in a lot of video game-based RL, there's been a lot of work to deal with the sparse reward problem by defining sub-rewards and a lot of reward engineering. Do you see that NLP RL field is going more in that direction, or do you think these rewards we have as just whether or not it gets the right answer and stuff like that are going to be sufficient?
For the questions we're using now, it seems or for the problems and domains we're using now, it seems the outcome is sufficient. And the support I have for this is the kind of papers that show sampling baselines to models without doing any RL training. So they look at the rate. If you ask the same model the same question thousands of times, you look at the rate of the correct answer. And even extremely outdated and small models like Pythia, 70 million parameters, will generate correct answers to this math, all caps, math 500 data set a reasonable amount of the time. And if we're trying to just like reinforce the ability for it to do that, it's very different than like a randomly initialized neural network trying to find something like that for the first time. So as long as we're in domains where things are close, I think we're gonna hill climb on that really fast. But then it kind of opens up the same question of like, how do you get AI to solve kind of unsolved problems that exist already?
Thanks.
Yeah, thanks for the talk. It's really, really amazing. So the transformer model is like it's really, really parallel to train, right? And so it's great for pre-training. It's not so great for inference, like the way that it's designed is just not very parallel in that regard. And you know, because it has to generate step by step. And so if we're scaling up this RL like a ton, do you think that that's a problem with the RL problems, or like is it just you can parallelize those across different things, or like is that a limitation of the transformer, and should we look at different architectures, or is it what are your thoughts on that?
I think it's a good type of academic problem. I think it's like the type of problem where you're like, oh, it's like, can we do something that like really makes people readdress the certain paradigm? I thought you were going to lead on to like, oh, and the diffusion language models do better because they generate really long context at all of inference for like a fixed inference cost, which is a fun question of like, can you train diffusion language models with this RL and not have as many infrastructure problems on long context inference? But it's like, it's like a fun experiment, and I definitely don't spend most of my time thinking about this type of thing.
Cool, thanks.
Anyone else? Oh, yeah, the back. Ian. Sit next. Yeah, time. We'll do one more maybe. We'll do sit next, and then we'll be good.
Okay, thank you very much, an awesome talk. I spend a lot of time thinking about confidence. And so when models are generating token sequences, I would really like to know how confident are they on the next token. And there's been a wealth of work in that area, even computer vision, speech recognition. But in the NLP world with the large language models, there's not much there today. And what is your sort of impression or feeling about how the importance of just outputting a sequence of tokens and having base models and using reinforcement learning to reduce the likelihood of hallucinations, let's say, compared to outputting additional information about the confidence of token sequences as you're generating them?
I think you kind of asked or you proposed it as a very important direction, and then you asked like two specific-ish questions. And I do think that people are using RL for factuality, and I do think that it is a way to help address hallucinations. It's a kind of complicated way, because you have a lot of like back scores and context to kind of have that in your training thing. And then almost like a product question with whether or not you want the model to have really high confidence or to actually just output whatever the confidence is. And I think that generally I lean towards the former, on having the models that can understand their confidence is such a huge unlock in a product sense. If you think about when you don't like using models, it's mostly because they just say gibberish. And if the model really knew its confidence all the time, the ability to just have like a calibrated answer with its level of uncertainty would be so wonderful, where it's like the answer is blank, or it's like, I'm like iffy, or like I'm just totally guessing. Like I'm gonna blabber as a language model because I can, but here's some tokens you should go text. Like I think as a user that would be such a huge change. And people talk about scaling, like improving the calibration of models in factuality literature, but I think that it just needs to be. It's almost like when the field matures more, then people will be like, okay, we really need to make these more robust, but it would be transformational.
Cool.
The RL factuality stuff is cool.
And today, the models will always sort of articulate their confidence on something, even if it's not there. And the second question, which is sort of orthogonal to that, is in a lot of the early search work at Google, etc., using neural networks for ranking of pages, they were actually using feedback from user clicks to update the models there and then. And do you see sort of a pathway of going from reinforcement learning that's done today to online systems where if there is an error and I correct it, and if you trust me, these models can get improved online, sort of over the lifetime of their usage, and just become better through being used.
I don't actually think parameter updates are going to be done online,
Yeah.
but there's architecture changes with knowledge stores that you can kind of sub in, or context that I think people will change. I think ChatGPT really, really, really heavily relies on context now. If you're doing GPT 4.5, it's like a little too strong. If you're used to using just like a vanilla model and you go to ChatGPT now, it's like you don't need to tell me that you know about my life. But if you think about that in a more general way, where it has like a general context that it's updating, it can work. It's just not something that's being focused on.
That's very cool. Thank you.
A lot of the RLHF literature is downstream of this preference stuff that Google did and stuff, which is fun.
Okay, we'll do one more with Sid, and then if you have other questions, you can maraud Nate in the 10-minute break we'll have afterwards, I think.
Thank you. So my questions are on long context reasoning. So at least in 2023, when I was writing prompts on 3.5, GPT 3.5, even though it had a 16K context window, it would barely follow like the first 4K and the last 4K tokens. So because of loss in the middle, which is the paper by Meta. So like 2 years down the line, I hardly hear papers addressing this as a problem. Is it because the direction is reasoning models will eventually solve the problem of long context reasoning, or is that a problem that people don't think it's important enough right now?
I think there's a lot of, I mean, it's like, there's definitely still a lot of focus on long context. I think it's like one of those problems where it's not necessarily easy for people to work on. It's a lot of hard data work, and then even more expensive to train your models than it would be, because most people don't train their models for long context in research. So I do think it is still, like I would say it's still an important area of research, that there are papers that come out that are very important. So I think that they are getting better. I think it's hard to know. I don't know if anyone here does, but it's like ChatGPT, when you pay more, you get longer output context potential. It's like one of the weird things about the Pro, or the Plus and then Pro tier, is that you go from like 16 to 32 to 128K context output length, or input length as well. So there's like really, it's kind of evolving in the background, but I do think that at least in the industry, people think it is a very high priority.
So my question is also around, like, even if it's a 120K token context, it's not going to actually follow those instructions exactly, right?
Yeah, that's like a fundamental problem,
Yeah.
where you can't ask, you have to ask it 10 things one at a time rather than one prompt with 10 things. And I am guessing that it'll be abstracted into, like, sometimes your general query will be handled like deep research, where the model is like, okay, I need to break this down into multiple queries and then get back to you. But for now, it's just not worth it for them to add that complexity.
Good. Because at least from a personal experience, I found often rearranging the prompt sometimes works. So
yeah, or you just like save part of your prompt for a follow-up rather than including it in the prompt, which is like so annoying. It's like, I don't want to do this at all.
Thank you.
Okay, thanks for the good questions, and for Nate for his knowledge and his stamina over the last 60 minutes. We're going to do a 10-minute break to stretch our legs, bio break, and get Dylan set up. So yeah, enjoy. We have some more food and drinks over there if you like. We'll be back soon. man. So I think, yeah, Dylan is a super interesting person to listen to, and hardware has, in my opinion, kind of been like the unsung or undersung hero of the last decade of success, and he knows hardware very well. So please put your hands together for Dylan.
Thanks, everybody. If there's anything that is unclear, literally just speak up. I'm fine with interruptions. We can just rip because I'm gonna, I don't know what your level of knowledge on these topics are. So I'm gonna talk about inference math and tokenomics.
Pointed at me. Okay, now try.
There we go. Yeah. Okay. Cool. We're gonna talk about inference math and tokenomics. So basically, like tokenomics is LLMs output tokens. It's the economics of that. And we're gonna talk about some key concepts like quantization, batching, parallelism, etc. KV cache. We're gonna talk about some of the reasoning models, and then the total cost of ownership of some of this stuff. So we're gonna get to the sort of merging sort of what's going on in the models with the hardware, and how it actually runs, right? So why do we care, right? For you just go rent GPUs, or you go buy tokens from an API provider, right? Or you go buy ChatGPT. But for them, it actually matters a lot how they serve it, right? And because a lot of models are basically fungible, right? They're open source models. You can go to any number of providers, and they'll end up being a fungible product. And so therefore, like the company serving tokens has to be able to make a profit because they're basically selling intelligence, right? And so this table, you don't need to, I'll explain stuff in here later. But the main thing is that there's a couple like key aspects here, right? One is like large language models are autoregressive, right? You have to read the entire model into your chip from memory into your chip. Do a couple matrix multiplies per parameter, do your KV cache, etc. And then that generates one token. You append it to the context, and you do it again, right? So you do it over and over and over, and therefore there is a huge cost associated to that, right? Of reading the entire model into from memory into the chip. Chips are very limited on memory, and so therefore you want to be able to batch, right? And batching means bringing many users together. And so that's the key, like that's one of the key aspects of sort of inference math, is you have to batch to be able to make it profitable, right? So there's a lot of other things that are interesting in this table, but the main thing is, at least for the mixed realm model, no one was making a profit unless they're batching more than 32 users at once. And the interesting thing is, like, once you know what your average batch size is going to be per sort of server, how many users you're going to be able to serve, you can then start to get to, hey, how many GPUs do you need to get so many X tokens per day based on inputs and outputs, right? So like you can serve basically the whole world with tokens just like on a million GPUs, right? Which is like on Llama 70, but no one wants to use Llama 70. That model sucks, right? It's good, but it's like just not useful to use. Sorry?
Llama 2 is 7B.
8B. Yeah. These are little tables. Come on, man. Nathan's giving me crap for using an old model.
I'm just saying Llama 2 was bad.
Llama 3, 8B is also bad. So I think like some of the things that are interesting to initially think about, right, is most models are trained in 16-bit. Some models like the labs, DeepSeek, they've trained in 8-bit. But if you're doing 16-bit, right, FP16 or bfloat 16, that's 16 bits. That's 2 bytes per parameter. And so if you're talking about loading, which model is this? Mixtral 8x7b, so I don't know how many parameters that is, but like, shoot, I don't actually remember how many parameters that model is. Anyways, you have to, there's, call it 50 billion parameters. If it's 16-bit, then it's 100 gigabytes that you need to load every forward pass if you're loading all the experts. And if it's in 8-bit, right, if you're using int8 or FP8, that ends up being 50 gigabytes, right? So it's a huge savings in terms of memory bandwidth when you're quantizing. And then different GPUs are going to get different sort of efficiency gains from quantizing. Of course, quantizing isn't free. It does reduce quality. So you have to pay special care when you're quantizing models. This is the primary reason why everyone quantizes models. Going back to batching, it's the same thing, right? If you're able to have larger batch sizes, your cost per tokens are much lower, right? Because you're serving way more tokens out, and so you're generating revenue for them while your cost falls per token because you're generating way more for the batch, right? And then this is like sort of like a more relevant chart, right? Like so as any like, say you have one GPU, say you have 8 GPUs, whatever it is, whatever model you want to run, you're always going to have this kind of curve, right? Basically, if you're running at batch size of 1, then you're going to have the maximum interactivity, i.e. tokens per second per user, so that one individual batch is going to be very fast, right? So for this model, you'd have like 40 tokens per second for that one user, which is good user experience, but it's really expensive, right? And then as you go up massively in batch size, it flips to, hey, I can have way more throughput per GPU, i.e. my cost is much better, but then my interactivity is really bad. So you have to strike the perfect balance on this curve for any given model / system. And so generally, like that's the big thing why people just batch to infinity, right? Because then it'd be really cost effective. Of course, you can't batch to infinity because then the chip starts running out of flops to compute with instead of just memory, right? You're memory bound most of the time on inference until a certain point where you're flop bound. And then there's also a lot of like interesting aspects of like, okay, models are getting way too big, right? Like DeepSeek is, I don't know, like 600 something billion parameters. There's no GPU, if you're running an FP8 that's 600 something gigabytes, there's no GPU with 600 something gigabytes of memory. So you have to run some sort of parallelism strategy. And so, today, right, like, with no parallelism, you can do like Llama 70B or Quen's models, right? You can do them on one GPU. But over time, you have to, as the models get bigger, you have to start splitting them up, right? And so the most simple form of parallelism is pipeline parallelism, right? Where you take a certain number of the wait, hold on. Oh, the table's screwed up. Oh well, whatever. So I was going to say that what you do with pipeline parallelism, this table is wrong, by the way. I got the wrong table in there. What you do with pipeline parallelism is you split the number of layers up. So you might do layers 1 through 60 on the first GPU, and then you do layers 61 through 120 on the next GPU. So this is great because you're getting all the benefits of splitting the model in half, but then you're not actually improving the speed of the inference, right? Because you're sequentially processing it on different GPUs. So that's like pipeline parallelism, but then there's tensor parallelism, where instead you're splitting up each tensor, right? Every single layer has massive tensors, and you're splitting them up across the GPUs. So then this is much more communication intensive because every single layer has communications between the GPUs instead of just between the 60th and the 61st layer. But then this ends up massively, it does give you the memory benefit, right? But it also gives you performance boost as well in the per user sense. So that's like sort of what tensor parallelism is. And then there's expert parallelism, right? With models nowadays, use a lot of mixture of experts models, right? Like DeepSeek. And so the same thing happens, right? People, instead of running, instead of doing pipeline parallelism, which is certain layers on different GPUs, instead of doing tensor parallelism, which is just splitting up the model, every layer on all the GPUs, you do expert parallelism where experts reside on different GPUs. And so DeepSeek, their paper was really the first open source implementation of, or description of someone running expert parallelism. But what they did is they even though their model was 600 something billion parameters, they could have ran it in 8 or 16 GPUs. Instead, they ran it on something like 320 GPUs. And that was like a very odd thing for them to do from most people's perspective. But the reason they did that is because they could extract a lot more efficiency by doing expert parallelism, i.e. each of their experts would sit on different GPUs. And so this helps with communications overhead. This helps with improving the interactivity or the tokens per second per user. Yeah. And then I think one interesting thing about these mixture of expert models, though, is when you're at batch size 1, right? Has this got a pointer? No. When you're at batch size 1, you only have to load how many experts there are per forward pass, right? So if there's 2 experts in the forward pass, 8 total experts, then you only need to load 2 of them. You don't have to load the whole model, which is great. In which case, then you're going to end up with loading only 12.9 billion effective parameters in this 50 billion parameter model, because you're only loading 2 of the experts. But as you sort of grow the batch size, then you have to start loading all the experts. So if you go fully, if you're doing a batch size of 64, you're going to load all 8 of the experts always, and so that's going to be 46.7 billion parameters loaded every time, which is going to be 100 gigabytes or so, right? But when you're in the middle, it's not like actually simple as that, right? So if you're doing a batch size of 2, you have 2 users, you would think, oh, I'm going to load 2 experts for each. But then you don't actually know ahead of time which experts you're going to load. So it's actually, because it's non-deterministic, right? There's a router at every layer telling you which expert you're going to go to. And so you end up with, oh, on average, I'm actually going to load 3.5 experts, right? For every inference, every forward pass for that MOE model, right? Because user number 1 is definitely going to load 2. User number 2 is definitely going to load 2. But a lot of times, one of those experts or both of those experts will overlap. And so on average, you end up loading 3.5 experts. And so sort of there is a bit of a weirdness with MOE models when you're batching. At very high batch sizes, you can just assume you're going to load all the experts. At very low batch sizes, you just assume 1 user, right? But then in the middle, there's a bit of oddities there. Data parallelism is pretty simple. You just run. It's replicas of the model, so it's not really, they don't really interact with each other. I think, yeah. And so one of the challenging things on infrastructure, right, is if you could with parallelism strategies, you would always run tensor parallelism, right? Because you get all the benefits of speed and memory, right? Whereas pipeline parallelism, you get none of the benefits of speed, and you still get all the benefits of the memory aspect, but you don't get any of the benefits from speed. So there's sort of one side is tensor parallelism, you get all the benefits of including speed, but pipeline you don't. And then expert parallelism is kind of in the middle. But then there's the other flip side, which is communications bottlenecks are a really big problem, right? Sharding the tensors is really, really expensive on comms, and there is overhead. And so you have to be aware of what your infrastructure is when deciding which parallelism strategy you're running for the model that you're running, right? And you should just never assume that models that you care about will run on 1 GPU in the future, because that's just hopeful, but very unlikely as models continue to scale, right? Like DeepSeek and such. Llama 405B, Llama 4 is going to be MOE as well, so it's going to be hard to run those models on a single GPU. So you have to pay special care. And there's different kinds of networks on chips, right? So for example, NVIDIA GPUs have 2 different networks, right? They have their standard Ethernet or InfiniBand network, and then they have their NVLink network. And so over the NVLink network, that network is 450 gigabytes a second, right? Whereas that InfiniBand or Ethernet network is only 50 gigabytes a second. And so there's a humongous difference in performance for these 2 networks. And so the parallelism strategy you run across them is also very, very different. Interesting thing is, new GPUs are going to have much larger sort of parallelism domains. They have much larger NVLink domains, i.e. you can run tensor parallelism and expert parallelism in up to 72 GPUs instead of just 8. That's currently possible in the sort of Hopper systems that people have today, and that's sort of upcoming GPUs from NVIDIA. And this is sort of like an explanation, sort of like a more realistic diagram of this, right? And so this is expert parallelism, right? You have your feed forward, you see there's expert 1 and expert 2 on the top and the bottom, and there's 4 GPUs here. And so you're going to do, this is tensor parallelism between GPU 0 and GPU 1, and then tensor parallelism between GPU 2 and GPU 3. But then there's expert parallelism between the first bucket of GPUs and the second bucket of GPUs. And this is just showing all the communications that happen on a single layer, right? Because you do your tension, you have it all reduced there, you go to the router, and then it decides which feed forward network to route to, and then you route it to the correct feed forward network, and then you do your tensor parallelism there, and then you do the all reduce and do an all-to-all communication, and you go to the next layer, right? And so in this case, right, because the tensor parallelism is only between GPUs 2 and 3 or 0 and 1. That's where you have extremely high bandwidth, sort of communications in the dotted lines. But in the otherwise, you're in between. Yeah, I think that's kind of self-explanatory. And so what's interesting is like when you're doing like various kinds of parallelism in inference, you have huge drop-offs in performance depending on what parallelism strategy you're running. And in fact, the optimal thing to do differs based on what parallelism what you're aiming to achieve, right? So tensor parallelism. This is 64 GPUs, like always, even though it says TP8, which is tensor parallelism 8. That just means there's 8 replicas of it as well, right? So there's data parallel 8 with 8 TP. When you're running tensor parallelism, you do get all the benefits of the speed, but then you lose performance because there's overhead from all the communications, right? So if your goal is offline inference, i.e., submit a bunch of documents to run in the background, and you don't really care if it gets done in 5 seconds or if it gets done in an hour, you don't actually want to run tensor parallelism that much, right? Because then that's way too expensive. You're incurring all this hardware cost of communications without actually getting any benefit from it. On the flip side, right, if you're running like, let's say, a code assistant type thing, right, where you're doing code completions or something that's very interactive, right, where you're constantly giving feedback to the model, you actually want to run extremely high tensor parallelism so you can get all the interactivity, but then your throughput is really bad, right? I.e., yes, I'm being served really well, but everyone else, there's not that many other people that are served alongside me, right? And so there's this sort of Pareto optimal curve of like what parallelism strategy you run on your GPUs based on what is optimal for what is the optimal based on the workload, right? What's the requirements? What's the SLA you need to achieve? What's the optimal configuration you want? And so basically, it's like a whole there's a whole simulation of it, right? Like there's many different types of parallelism strategies, and not all of them will be Pareto optimal, right? But some of them will be, and that's sort of what you're sort of charting at the top. Yeah, I'll talk about KV cache now. I don't know how much you guys know about KV cache. You guys talked about that much?
Yeah, a little bit.
I see a couple of head shakes, so sounds good. It's your key value cache. Yeah, I don't know. It doesn't seem like it's worth explaining then. Enough head shakes.
I think you can explain it. I mean, it's,
Yeah, I mean, okay, sure. I'll talk about it from like a hardware perspective, right? Like, what's fun about KV cache is there's sort of 2 stages of it, right? Like, yes, it is it's the attention between every token, right? Right? You need that to run your transformer. But what's interesting about it is when you're calculating your KV cache, it's completely parallel, right? So while inference is very sequential, i.e., every token is generated, when you're calculating your KV cache, when a user submits a long prompt, say there's a document in there, that's actually extremely parallel. That's actually a batched workload, right? Because it's like I'm calculating 10,000 tokens at once instead of 1 token at a time. And so sort of the KV cache calculation size is sort of up there, but basically it all boils down to sequence length, right? And sequence length, the longer it is, the larger the KV cache ends up being. In which case, that if we go back to our whole point around like memory is what's the bottleneck in inference, then memory is what's limiting your speed of inference. And so the longer your prompt is, the longer your context length is, the slower your inference is going to be. And so for a given model, at a given precision, et cetera, scaling context length is only going to make you decrease your batch size, right? Because then you're going to run out of memory because the KV cache is taking a bunch of memory up. So for example, you can only fit 8 users if the context length is like 10K, but if the context length is 4K for all of them, then maybe you can fit a lot more than 8 users, right? And there's a lot of innovations that people have done. No one does the standard attention from the Transformers All You Need paper, right? There's all sorts of stuff like GQA, MQA, MHA, and now DeepSeek did MLA, right? So there's all these different attention formulas or sort of like, mechanisms that are much, much more efficient now than the standard attention from the Attention is All You Need paper. But they still all have the same sort of sad aspect, which is that they all scale quadratically with attention, context length, right? So still, scaling, your context length up 2x is going to scale quadratically in memory cost. So yes, GQA, MQA, DeepSeek's MLA are very efficient and huge improvements over standard transformer attention, right? I think DeepSeek's is like 97 or 93% more efficient. It still scales quadratically, and so inference is still a memory limited aspect, right? It's still memory limited. And so what's fun is you can sort of see the benefit that you get from GQA versus standard attention, right? And you can do this for all of the different types of attention to sort of chart them out. You don't, it's not really that. GQA is not really going to help you that much in training. The primary reason you do it is for inference, because in training your batch sizes are massive and you're not latency sensitive anyways. But in inference, you are very latency sensitive, and you care about your batch size being as large as you can. And so this chart sort of shows that your interactivity, i.e. your token throughput, is much higher when you have GQA at say a batch size of 16 or 32 than it is without it, right? So there's huge, and that's primarily because GQA is dramatically reducing your memory. But yeah, going back to the point, yeah, it's still quadratic regardless, right? And this is really important as we go to reasoning models, right? Reasoning models are longer context in general than standard models, right? Standard models, you tend to use them for chat style applications. You throw in a few, you maybe throw in a question, you get some, get 500 tokens out, or maybe you throw in a whole document and you get like 500 tokens out, or whatever it is, right? Or you ask it to generate an essay, whatever it is, right? I don't know, you guys probably generate essays all the time. But the reasoning models, while they do end up with their response looking very similar to what the chat style model does, they have this whole period of the thinking, right? The reasoning chain that they don't show you, the OpenAI doesn't show you, but DeepSeek will show you. I think Anthropic shows you. I think XAI shows you. I don't remember who else shows the reasoning chain to you. But you end up with tens of thousands of tokens of thinking / reasoning, and that whole time the context length is growing, right? So maybe your question is, help me write X, Y, Z, or what's the answer to this math problem, right? And then it's just generating tokens and tokens and tokens and tokens. And then when it's close to its answer, its context length is now 30K, 40K, and it gives you the answer. But in that meantime, those last 10 tokens it's generating, it has to pull the KV cache for the whole 30,000 token context length that it had, right? And so reasoning models have huge memory requirements that are much worse than standard models, right? Because inference is already very memory heavy, but then because reasoning models have long context length, in addition, they're even more memory heavy because they have to load all the parameters plus this massive KV cache. There's a lot of different optimizations out there that people are coming up with, and I think that's like an area of research. I don't know if you folks do research much, but there's a lot of interesting research out there on this, on improving efficiency in inference, and it's probably the area where the most exciting papers are published, in my view. So I would say just go on archive and grind those kind of papers. And contribute in that area. And it's also something you can do even if you only have like one GPU to play with. This is kind of dated because this slide is kind of dated. There's even more interesting stuff that's come out since, but I won't talk too much about that. I guess I'll talk about '01, right? And this is sort of going back to what Nathan said, although this slide is old, right? We didn't get big models when we finally got, in that orange circle. When we finally did get a big model, right, it was GPT 4.5. It was kind of disappointing, right, for a lot of people because it wasn't like, because it was 10x bigger, but it wasn't actually like that great. It was better, but the reasoning models are much better. And again, Nathan talked about this, so I'm not going to talk about this slide, but yeah, test time, training gives, the scaling laws for training are still true, right? A log increase in compute still gets you that same improvement, actually, and the labs still don't see it. It's just that's so expensive, right? Going from $300 million spent to $3 billion spent to $30 billion spent, right? So it's sort of like diminishing returns in the sense that like human capital is involved, not like, or like capital is involved, not that like the scaling laws don't work anymore. It's just too expensive. And so reasoning is like a really good, or test time compute is a really good way of going about it. And so, yeah, the traditional inference generally, what is this? Yeah, so this kind of goes back to the sort of the thing I was mentioning earlier, which is that with standard inference, it's you have lower context lengths, and you often have you have two phases in inference. You have prefill and decode. So prefill is when you're processing the prompt. Decode is when you're generating the tokens incrementally. But that ratio matters a lot too, because if you have a lot of requests coming in and you're batching, even if you can't get enough users to batch to utilize your GPUs effectively, all the prompts that are coming in you can overlap and sort of use up your compute effectively over time, right? Because all these users' prompts are coming in and you can do the prefill on them on the same GPUs that you're doing the decode on. But with reasoning models, your prompt is very small relative to your total tokens generated, and so therefore you can't really overlap these prompts on the decode because they're just kind of insignificant in total cost and total compute. And so that really makes reasoning inference like really annoying to do because that ratio of prefill to decode falls dramatically. And then the other thing is that like you don't get to amortize your KV cache, right? So your parameters, you get to, as you increase batch size, you get to amortize them across everyone else, right? Because you're loading the same parameters for me as you are for you, for you. But with your KV cache, it's individual to each user, so you don't get to amortize that cost of loading from memory. And so then you end up with on a reasoning model like '01, right? If your context length goes from 500 to 10,000, or I don't remember what numbers I used here. I think I did 16K. Oh no, sorry, from like 700 to 30,000, right? If your context length grows a lot, your number of users you can serve, even if it's the exact same model weights, the number of users you can serve is much lower, right? So '01 and '03 are the same model architecture as GPT-4o, right? Same size, same number of experts, etc. The model weights are different, right? Because they did the post-training for Strawberry, but the model size is the exact same. And the architecture is the same. It's based on the same base pre-training. It's just that post-training is all different, right? And so, yet despite this, OpenAI charges something like, I want to say 4 or 10x more for the reasoning models than they do the regular models. And part of that is like them like making money, but a lot of that has to do with the inference economics here, right? Because the batch size falls so much because the reasoning models have so much longer context length, the batch size falls, now the cost increases dramatically, right? Because the same number of GPUs that we're serving, potentially 256 users, are now only serving like 16. And so you need to make up for that by charging just a lot more per token. And so that's where a lot of these, DeepSeek's innovation on sort of like MLA and latent attention is not that relevant for regular models. It's actually not that important, but for reasoning models, it's incredibly important. And that's why we need sort of these, long context sort of innovations, or subquadratic attention sort of research is not for standard chat style applications. It's all about for reasoning and for agentic tasks, where context lengths do balloon to massive, massive sizes. Because then the memory cost of all that KV cache starts to dramatically reduce your performance, not just on batch size, but also on an individual user basis. Yeah, prefill versus decode. I don't know if you guys know that or already. Cool. Also at long context, the flops from scaled dot product attention actually dominate the flops, not actually the cost of the reads. Yeah. Yeah, I think that's. I won't get into the inference simulator. It's quite complicated. I don't know if you guys want to talk about that, or we could just talk questions.
What's the just like
It's inference simulator. So quickly, it's sort of just like a simulator that we built to run models. Basically, like if you know your model architecture, you can input what hardware is there. You can input what, and you can sort of do a scan of like, hey, input versus output. What's the prefill versus decode ratio? How many users? You can scan across different parallelism types, and then you can start to see like what's the cost of running inference on any individual model, right? So you can vary your GPU, you can vary your model architecture, you can vary all these things, and then it'll sort of like output what's the best, what's the most efficient inference system, or what's the cost, et cetera, right? That's sort of what this inference simulator is. But I don't know if I want to talk about all that. Might make more sense to just ask random questions, including some of the questions that y'all had for Nathan that aren't really that he sort of said would be better for me to answer.
Yeah, sure. We can go to questions. Should we have a clap first, maybe? While people are thinking of their questions, I have a quick one. I guess going from like the non-reasoning models to the reasoning models in the past, people put a bunch of compute into these models at training time, and then after training, for people who are actually doing inference in the models, somewhat less compute required than now with these long reasoning chains. How does that change, I don't know, I guess like the competitive landscape, I suppose, with respect to like neoclouds and people who want to host their own models as compared to super GPU-rich frontier labs who do inference stuff also?
Yeah, so there's the...
Maybe one of us at a time.
Hello?
I'll give you this.
Okay, no worries. I'll just talk about it. That's fine. So there's the whole like thought that like no one should be pre-training besides very rich companies, right? But for a while, especially in like 22, 23, a lot of companies were pre-training. But companies that were pre-training are like, mostly doing poorly if they're not the big companies, right? Companies like Mistral and Inflection and Adept and all these folks are either dying or dead. And so, obviously pre-training, it quickly became a game of like scale wins. But now we have a new class of sort of companies that have been popping up, right? They're saying we're not going to do any pre-training at all. And we're going to do only post-training on verifiable rewards, right? And so, there's like dozens of companies like this. And there's also very large companies who have raised, couple billion dollars, like Thinking Machines, which is Mira Murati's company, or SSI, which is Ilya Sustover's company, which is not enough to do pre-training at humongous scale, like what OpenAI and Anthropic and those guys are doing, and XAI, et cetera. But it is enough to do post-training. Like reasoning, so the question is like, how does this sort of like change the landscape? Is that like these companies can exist, but not just that, right? Before, to get a more intelligent model, you would just need to train a bigger model, right? But now, to get a more intelligent model, you can take a model that's already been trained and you can scale it across multiple axes, right? You can do search, right? I.e. run multiple inference streams at the same time, whether it's best event or some complicated thing like Monte Carlo, or you can do longer reasoning chains, right? And models have shown to improve on both of those. The thing is, you don't just get reasoning models for free. You have to teach models how to reason, and that is expensive as well. And it is, there's sort of like, I talked with Nathan about this a while back, but basically like, it used to be you called it pre-training and post-training, but in the future it's just going to be like pre-training and training, because post-training is going to be such a large percentage of the compute dedicated. And as far as like how that changes the landscape for compute providers, this is very helpful for them because like, you can do reasoning on smaller clusters, and it doesn't need to be this humongous 100,000 GPU cluster.
For people to talk about how like the capabilities are growing, but a lot of users' demands and users' problems that are being solved with language models are not getting necessarily harder over time. Answering my email, writing my essay, et cetera, type things. So if you can have a smaller model that you can serve, it just generates more tokens that could perhaps, be useful for.
Well, so the funny thing is, reasoning is stupidly expensive. Like it's like if you run like GPT o1 or o3 mini, whatever, and you run it through the API, they'll generate 10,000 tokens and they'll charge you for every one of those tokens. And it's really, really expensive. Like your cost per query is like quite high. So like the strategy of like, oh, I'll take a small model and I'll do reasoning is actually like generally quite expensive versus like, oh, maybe I just take a model that's 10x bigger and I don't need to do reasoning. So it ends up being like reasoning models, you don't do reasoning because it's cheaper. You do reasoning because it gives you a capability that you didn't have before. In which case it enables new use cases, whether it be like automated coding or what have you, math, etc., right?
Last follow-up, do you have any quick sense in terms of like 7B models reasoning versus the 32B non-reasoning model, maybe perhaps similar performance? Which one ends up being more or less expensive? Do you have any idea on average?
A 7B model versus like the 32B like Quen model that just came out, or what do you mean?
Smaller reasoning model versus a larger non-reasoning model. The question, you were saying we don't do it for the purpose of saving money necessarily, but in reality, do we save money on average? Do you have any idea?
Yeah. So I mean, I think there's also the constraint of like a 7B reasoning model can be run on a phone or on a laptop, whereas maybe a 32B reasoning model, a non-reasoning model can't be. So there is that aspect. And so like, but generally, also Nathan mentioned this earlier, right? But like models, you're not going to have reasoning and non-reasoning models in the future. The model will just know how much to reason. And this already exists in base models today, right? Like if you ask it to do, if you ask like GPT-4 to do something, oftentimes it still generates some chain of thought, right? It's not tens of thousands of tokens of chains of thought, but it is some chain of thought. And Claude actually, like, if you can like turn on the reasoning mode and vary the length, and it knows how much to reason before it gives you the answer. So we're already getting closer and closer to the point where models will just be, it'll just be a model, right? And it'll know on its own how much to reason. But in the meantime, definitely, in general, I think a 32B base model, if it's capable of doing the same thing as a 7B reasoning model, then the 32B base model is going to be cheaper to run. Because it's going to deliver the answer way faster, sooner, because it's outputting like 10x less tokens.
Thank you. I'll go to Jeff over here.
Yeah, awesome talk. Yeah, I really liked it. So I have a really kind of basic question with the communication, like the networking. So I don't, this isn't something that I think a lot about, training these huge models or doing this. And I imagine the different kinds of parallelism obviously have different communication loads, right? Like data parallel is super simple, but like tensor parallel is going to be really high, like a lot of communication requirements. So what, I just want to get a sense of like how much we're limited by the bandwidth of the communication between the different nodes in like a huge network that's training or doing inference for a large language model. Is that something you think about, or is that like, yeah?
Yeah. So the question is basically, how much is the networking actually a limitation? And in most cases today, people don't just think about it, right? They just don't think about it because their models don't care. Like Llama 70B, you just run on one GPU. Llama 405B, you run on one node, etc. But it does become a huge bottleneck. So if you read, like, for example, DeepSeek's papers, they spent inordinate amounts of time worrying about the networking, right? Even though networking is not even limited by the US export restrictions, right? Like the NVLink side or the InfiniBand side is not limited at all. They still spent inordinate amounts of time on the networking because it is a big bottleneck. You end up with, there's sort of like three, if you boil down like training or inferencing a model, there's like three things, right? There's reading from memory, there's sending traffic between chips, and there's compute, right? in an ideal world, you're only bottlenecked by compute because the other two are hidden, right? They're overlapped, right? You overlap your communications and your compute. You overlap your compute and your memory reads. But that an ideal world is like really hard to achieve. You know, there's all this stuff there, right? So I would say, what like I guess the question is like when would you worry about it, or?
No, it's like what order of magnitude are we talking? Like in terms of the communication between in the big network, like how I realize within the chips, that's
Yeah, okay.
bytes. Like what?
So it also depends a lot on model architecture, right? So Meta's shown like they have papers like some of their Rexis training. We're talking about transformers, but a lot of their Rexis recommendation system training has communications is like 40 or 50% of the time, right? It's not compute limited. It's actually just limited by network. Now transformers are a lot nicer because they are so much more compute heavy that they're limited by communications a lot less. But even then, when you look at like the Llama model, I think the Llama model ended up being like 20-30% of the time it was just waiting for network, right? Which is a humongous like inefficiency. And they spent a lot of time optimizing that, right? If they didn't optimize, they even talked about how they wrote their own communications library that was different from NVIDIA's base one, right? So if they didn't do that, then it might have been even much higher, right? So I think the communication sides of things is very, very, very big deal. And then on inference, this is sort of why Meta's talked a lot about why they run Llama 405B exclusively on AMD, right? And they do that because AMD has enough memory to fit the entire model in one GPU, or in one node, right? Unquantized, right? Llama 405B fits in one 8 GPU node from AMD without quantizing it, whereas it takes 2 nodes from NVIDIA. But the question is like, well, if it takes 2 nodes from NVIDIA, well, those 2 nodes have twice as much compute. Shouldn't they just have twice as much output? And it's like, no, the network bottlenecks are what's limiting you because they have far more than enough traffic to need tens of thousands, if not hundreds of thousands of GPUs serving the model. Right, so it's not like it's like a number of GPUs thing. It's just that parallelism strategy does incur a lot of overhead.
So when you implement different parallelism strategies for different models, do you design a parallelism strategy for each model, or you can, for example, you have strategy there and just use the model as a function parameter thing, and
yeah. So the question is sort of like, can't you just use the same parallelism strategy for every model? And I don't think that's not really possible because every model, you actually, even for one model, GPU to GPU, you'll have different parallelism strategies, right? So like for example, in OpenAI's infrastructure, right? They have A100s, they have H100s, they have H200s. And now they're going to have, they have some AMD chips as well, and then they're going to have Blackwell GPUs as well, right? 5 different GPUs, all with different memory bandwidth, all with different memory capacity, all with different network, sort of parameters on their chip, right? Whether it's NVLink side or Ethernet/InfiniBand side. So all of these parameters of the hardware change, right? And meanwhile, I've trained one model, right? My GPT-4 is X, right? Whatever parameters, however many other experts, etc. So the optimal thing for them to run on every piece of hardware is going to be different.
Also, that means that even if they release their model and we have our own GPUs, we need to write our own parallel strategy for those models.
Exactly. So because and you can see that with DeepSeek, right? DeepSeek, when they released their model, they talked about their inference setup, which was this 320 GPU expert parallelism strategy. No one wanted to deploy that, right? Everyone wanted to just be like, okay, we'll just do tensor parallelism 16 and call it a day, right? Or tensor parallelism 8 and pipeline parallelism 2 and call it a day. Instead of worrying about figuring out how to do expert parallelism. Now their systems are much less efficient now than what DeepSeek implemented, but they were able to run it on a different, on different hardware. And so and it goes back to sort of the that's too late. Oh, whatever. There's this. I think I can find it. Did this change it? No, it does not change it. Oh, okay, no worries.
What are you trying to go to?
I was just going to go to one of these slides. Yeah, this slide.
Here, you can use this now, but it's reflected back there.
Okay, no worries. So it kind of goes back to this sort of slide. What exactly? And even if you have even with static hardware, right? Your parallelism strategy will change, right? So you're going to have many different sort of search spaces, right? What is the interactivity level you want? Okay, that's gonna influence it even on static hardware. What is the type of hardware you have? That's going to influence what kind of parallelism strategy you're going to have. And of course, the model architecture you have is going to affect it too. So it's a very large search space, and that's why this slide right here is showing that search space, right? Each of those blue dots is a different parallelism strategy, or a different parallelism strategy at a given batch size, right? And so you end up with every single one strategy will have a curve like this, right? And then another strategy will have a curve like this, right? So each strategy will have different curves, and depending on where you are on batch size, how many users, etc., there's an optimal strategy.
Yeah, thanks. Actually, I see a lot of system optimization, like batching, like parallelism, but previously we also deployed this kind of strategy in traditional DNN network, right? So they will have some problems, maybe bubble for the pipeline parallelism. Will there be the same problem in this when you serve this kind of large language model? If it actually is, will they be different?
Would what be different?
Will this kind of problems, maybe bubble problem?
Yeah, so there's a lot of papers around pipeline parallelism, bubble stuff, right? No one likes doing pipeline parallelism, right? But there's a lot of in training especially, there's a lot of papers out there. On inference, there's a lot less papers out there for transformers. But there's zero bubble papers out there already. Yeah, I mean, it applies to all model architectures. How you do parallelism matters, but it matters especially. Transformers are just some of the first models where inference is such a difficult problem. Rexus also had a lot of challenges with inference because the embedding tables were so large, and so you had all these challenges. But I think it's similar ML system stuff. It's just a different problem set, and so you have to optimize it. Good.
I have another question.
Yeah.
So before we talk about, I think it's the last one. We talk about there's a diffusion model that can also generate the text, right? Mm-hmm. So in this kind of diffusion model, you don't generate the token one by one, right? So there will not be kind of a memory consumption issue here. Mm-hmm. Do you think that will maybe the solution for now the reasoning model have for the memory problem?
Yeah, so the beauty of the transformer is not necessarily it's absolutely disgusting that we have to generate each token, right, individually. But the beauty of it is that as it scales larger, your performance increases in a much better way, right? When you look at LTSMs, actually they outperform transformers at very small sizes, right? You look at some other models, in text they outperform transformers, and it's because that you can think of it as scale versus performance. As you scale up, that curve for LTSM looks like this. The curve for maybe another architecture looks like this, but the scale for transformers looks like this, right? I.e., as I continue to scale up, the performance gets better faster than any other architecture. And so that's why everyone has fallen in love with the transformer. And even diffusion models, right? If you look at the image diffusion models out there from, for example, Stability, and I can't remember the Black Forest Labs, I don't remember their model's name, Flux, is it, or something? Black Forest Labs, and then also there's research from Google and others. The scaling laws of diffusion models are quite poor, right? Same applies to CNNs, right? Making humongous CNNs does not give you great vision performance, and in fact, at some point, vision transformers outperform CNNs, right? Of course, CNNs are far more efficient at smaller scale. And I think this likely applies to diffusion models as well, at least just based on the scaling laws of diffusion models, right? Midjourney's largest diffusion models are still only tens of billions of parameters, right? They haven't scaled them to some huge degree because there's no benefit from that, from scaling larger and larger. So how much intelligence can you actually get into a diffusion model is a question as you scale it. And I mean, it's an open research question, right? If you can just make diffusion text models, that would be really, really efficient. But people are still like operating on the small scale. We'll see what happens as they scale them up, and there's a lot of research to be done. Maybe it is the trick, though, right?
So I had a question about the inference simulation thing.
Oh, did I accidentally press it? Sorry.
Just tap it, yeah.
Okay. Yeah, I have a question about the inference simulation. So, does that work? Is that like different transformer like shapes, or does it also do like if I had some crazy modification to the transformer, would it? Like,
Yeah. So the inference simulator we built, every single like the inference simulator we built, every single new like transformer technique has to be programmed in. But like shapes is the easy one, right? Like that's built in from the start, like right, like vary your hidden dimension. How does that affect your inference? Yeah.
We'll do one last one.
Okay, yeah, mine will hopefully be quick. This isn't really my strong suit, so I apologize if this is kind of like a low-level question for you, but I've kind of been really curious about, like, I know a lot of models train with student forcing, and I've always thought that, like, that would just be horribly inefficient, but I haven't really, like...
Student forcing?
But don't they usually use student forcing towards the end of training? Like, based on their own output? Or is that only done in inference?
I don't know what teacher or student forcing is.
Oh, okay. I guess
Is
student
this like an
forcing...
RL thing?
It's like where you take your last output as, like, the one that you're using in the decoder to predict the next one. But I would think it would make it, like, a lot less parallelizable, and I was just wondering if you, like, could fill me in on that, but it seems like it's not a... Okay.
Yeah, sorry.
No worries. If you have any other questions, we had another short 10-minute break where you can mob, I'm sure, Dylan for that. Oh, Alessio, what's up?
Do we want to do my talk, and I'll keep it quick, and then maybe we all just get together?
Sure.
Because I think we're already 20 minutes late, so
Oh.
I'm sure maybe
Yes.
I know you gotta go. I know you definitely gotta go.
Yeah, for the sake of our speakers, yeah, sure, we can go straight into the talk if you like.
Yeah,
and we'll...
I can kind of like, I just want to run through things, and then if you have questions, we can chat, and you can chat amongst yourselves.
Sounds good. Great. Well, as you're getting set up, I guess I'll tease coming attractions maybe, which we'll do, I guess, after Alessio's talk. So 2 years ago, I know a lot of people here are students that have gotten into ML in the last 2 years or so. I'm sure industry professionals as well owe a lot of their success to models that have been released in the past 2 years. So this actually marks the 2-year anniversary of both the GPT-4 model as well as Anthropic's Claude 1 model. So we have, if you can direct your attention over there, we have we have a cart with a quite expensive birthday cake for both Claude 1 and GPT-4, which is kind of a fun gag thing that we have. So look forward to that after Alessio's talk. We'll get him up and going first. But of course, if you have to take a short break, we understand. But we'll probably get started here soon just for our speaker's time. Oh, is that working?
Yeah.
I'll give everybody like 1 minute. But I think 10 minutes is like quite the break.
I was also very bad at the 10-minute timer last time. I was too generous.
You're good.
My critical.
All right, 60, 59, 58, 57.
Thanks. I know.
Yeah, no. It's good. I think it's easy to like when you break.
Yeah.
I'm so sorry. I didn't even realize I was going to
cut it up and hand it out, but I think
You're not a pro
people kind of
yapper.
see.
You're a pro prompt modeler.
Yeah, so I'm gonna leave it.
My bad, dude. I'm so sorry.
No, it's good. I'll see you around GDT.
For sure.
Thanks for coming very much. Thank you so much.
Thank you. Thank you.
Everybody, thanks for coming.
I got a lot of things in the slides. I don't know what people get about, but I'm just gonna run through a bunch of things. And then we can just,
I mean, this is what I was hoping you'd present on, so I'm satisfied already from the title slide.
Exactly. Well, you asked.
Yeah, sure.
It's like, I'm down.
Thanks, man. Yeah, you have something after this, I suppose, probably as well, or are you going faster?
Well, I just got things.
Of course.
General. Nothing, not one thing.
Yeah, just the constant grind.
Yeah, tomorrow we're hosting a personal agent hackathon at AGI House.
Oh yeah, I saw it.
Yeah.
Nice, congrats. I was joking about this, yeah, being the stepping stone to that one, right? Escort, yeah, for sure.
I need to give a talk there too, but I don't know what that's about yet.
Have you ever been before?
I've been there before.
What's the vibe? I kind of like, we're in Bay Area, I just moved here. But I haven't really been to like the SFTC yet.
Well, this is in Jonesboro. It's just the first time.
Yeah, there's a lot of stuff. So you're getting rid of that stuff.
Just need to
Good talk. Just running
I'm co-hosting.
Over in Stan.
Well, they do busy like they started to brunch and then 5 minutes talk. Like inspiration.
Yeah, and it is a short break. Yeah. I'll call people back about that.
Could I get a quick question right now, or
So again,
wait later? I was wondering about.
All right, our friends over in the eating area. If you would slowly make your way back over here, that'd be great.
Are we in the
Thanks so much.
direction towards building smaller reasoning models? A couple of years ago, we had a choice between 3.5 for inference versus fine-tuning of Vicuna. And Vicuna was better at coding tasks. And then right now, to beat the state of the art, you have to essentially build a bigger model. So, are we towards building smaller reasoning models which are just good at one specific task rather than like I don't want a coding model to be good at essays.
I'll work that in. Make me know where. Cover that. And,
Thank you.
I think people will come back as they.
No, it's all good.
I'll start now. All right. This still works. All right, everyone. It's always tough being the last talk of the day. And I got an expert in models to start, and then we got an expert in infrastructure, and then you got an expert yapper as number 3. So I'm Alessio. I do a couple things. I host a podcast called Lit in Space, which is the largest AI engineering podcast. We also run the AI Engineer Summit conference, which runs twice a year, which is the go-to place for engineers, so which is a new practice which my co-host Swix coined a couple years ago with a post called The Rise of the AI Engineer. And the idea is, maybe it's not the right crowd since you're doing an NLP master, but you don't need to build models to be an AI engineer. You can just consume the models. On the podcast, we kind of talk to, everybody that is doing interesting things in AI, usually well before they become interesting to the general public. So, we had Cursor on the podcast 2 years ago. If we invested, we would have made a lot of money. We had a lot of, we have Dylan before he became famous. We had Nathan. He was already kind of famous, but yeah. So if you care about what Dylan and Nathan care about, we have 2 previous episodes with them. So you can always go back and listen to it. I also run a venture firm called Decibel. At Decibel, we do early stage investing in technical founders building technical products. We have a whole lot of companies in the AI space that is both at the infrastructure level, at the agent level, and at the cybersecurity level. I think, as you might hear lately with all the news about geopolitical tension and all that, every system is becoming digital, and running an AI model is not just generating text, but sometimes it can be a lot more mission critical. So there's a lot more interesting in the space too. The reason why I'm here today is about this idea of the 4 wars of AI that we coined in our December 2023 recap. So there's basically 4 things that matter. One is the quality data wars, we call it. So you might frequently hear the models are trained on the whole internet. That's obviously not true, because the whole internet is not available for you to train on. So there's a lot of disputes on what data you can actually use, and we'll kind of cover that quickly. The GPU rich versus the GPU poor. Dylan Patel came out with that. So if you're GPU poor, meaning if you do not have hundreds of millions of dollars to spend on hardware, should you even bother trying to pretend to be GPU rich? Or should you just focus on problems that are more attainable for you as a GPU core. The multimodality we'll cover very quickly, but today is maybe a little less relevant, but it's the idea of like, should you have one model that does everything, or should you have specialized models, especially in multimodality? So, you might remember OpenAI's GPT-4o image generation. They never released that. I think Google Gemini got in some problem with their image generation model. So a lot of the multimodality is like very, how would I call it, delicate, both from a copyright perspective and from like a, offensiveness perspective a lot of times. And then we used to call this the RAG ops war, but then RAG didn't really matter anymore. So now we call it the LLMOS. So what are things, everybody understands models, but the difference between two models is often in how they get instrumented and how they get served and how people build around them. So that's another interesting battleground, so to speak. So I create all these nice images with Midjourney for the backgrounds, but on this projector, you cannot really see them, but I'll send them after. So there are three things that matter on the data side. So the walls are coming down, so to speak. So if you recently ended up on Reddit through Google, you might have seen like a highly increased amount of captchas. Like it used to be that you just open Reddit and it works. Now often I get like, are you a human on top of it? And you might have seen their stock price went from like 2 billion to like 20 billion. And a lot of the revenue is coming from the large labs buying their data for training. So nowadays, Reddit sells their data to OpenAI, to Gemini. XAI is using the Twitter data to train, which, I think Elon is trying to figure out how to get the 40 billion, written off eventually through value. And then you have the other side, which is if I have data that is in the open, but it's copyrighted. So for example, law data is very interesting because a lot of cases end up being public for both education and things like that, but it doesn't mean that it's up for grabs for you to train on. So there's this case with Thomson Reuters and Ross Intelligence on whether or not you can actually train on these things. And last, this was actually just recently confirmed, which is basically to get copyright, you need a human to author something. So if you just put a prompt in a model, the output is not copyrightable. I guess what's left to figure out is like how much work do you need to do after the model generates it to make it copyrightable. So these are kind of like the three main things that all the model labs are kind of struggling on. So yeah, if you try and use Sora, for example, you often get rejected for prompts that are very benign. For example, I was trying to do a podcast intro, and it's like I put my photo, and it's like make this person walk out like a TV show host. And Sora's like, this doesn't fit our guidelines. I'm like, that literally didn't say anything. It's very basic. So this and the multimodality wars kind of go hand in hand, but nobody really cares because we don't have anything to do. And then the other side of it is like distilling, people call it. Like, can you take a big model and kind of distill out of it? And OpenAI first trained everything on the internet, didn't ask anybody, and asked like, DeepSeek copied us. And it's like, you're trying to kidnap what are rightfully stolen. So this is another side of, OpenAI has a lot of lawsuits against them from like the New York Times and all of these publishers, and whether or not they actually end up, I don't think they're gonna sue DeepSeek, but there's no legal precedent of like how much data you can distill, and number two, how you can prove that you can distill from a certain model. GPU rich versus GPU poor. So the GPU rich, we're still back, right? It's like, like Nathan was saying, scaling is dead in Europe, and like Ilya saying all these things, and then Sam releases O1, it's like the smartest model ever. Actually, instead of $20 a month, you're gonna pay us $200 a month. It's over for you. Literally like a few weeks later, it's like R1 comes out, and it's like, NVIDIA stock goes down, and it's like nobody needs GPUs anymore, which is obviously not true. But it's really impressive that we kind of hit another step function on the GPU core side, which before it was like, how good can you make Llama, which is not that good. But now with R1, it's like you can actually use R1.1 to distill models. So you can take R1 and distill that into a Quen model or a Llama model. If you're interested in that, we have a talk. We have an episode on our YouTube channel about R1 distillation, which is like 45 minutes long. So I will not go through it right now. And then the other thing is like things just move very quickly, and I think sometimes it's important. Let me make sure the next slide is sometimes it's important to remember what was good before. So if you go back 9 months, a lot of people were building products and they were selling things and they were making money, and the performance of 9 months ago is now available in open source. So it doesn't mean that you have to keep chasing the frontier. Like a lot of times you don't need the frontier. All that matters, like, how do you build infrastructure around the model, and how do you make that useful for you and for your use case? Sumit Chintala, who created PyTorch, he gave a talk at our AI Engineer Summit, and his #1 kind of passion project is like personal AI agents. And he was very excited about where the future is going, more, especially on local inference not being a bottleneck anymore. So for example, this is the Llama 3 8B model performance on some of the newer MacBooks. You can run models at a decent speed locally, and the example he gave is like, look, I love models that are on the API, but sometimes there are things that I want to ask a model that I wouldn't want the thought police to know in the future, and this question I always want to ask to a local model, and I think everybody has their experience, especially in personal things. And if you don't have enough, like you might have enough to run inference, but you might not have enough to train or to fine-tune a model. And we have News Research, which is a good friend of Latent Space, and they trained this model called News Distro, and the training was done completely distributed from different users. It's basically like if you had a PlayStation 3, you might remember folding at home on the PS3. This is like a similar idea. It's like basically you just spread the training across a lot of computers and just do a model that then people can share back. Decentralization is like the core part of the personal agents. It's like instead of having to opt into the OpenAI ecosystem with deep research and search and operator and all these things, I can just build my own things in different domains, and I don't have to pay $200 a month. And most importantly, I can do things that OpenAI is not allowed to. If you're building personal agents, this is kind of like my personal agent anatomy. So you have a model, LLM, and a memory. So the LLM, it's almost like the LLM is like solved, right? Like there's plenty of good models that you can plug in. What's missing is really like all the other stuff. So web search, there's like companies like X in that space. Code execution, there's like E2B, there's like obviously a local Docker container. Computer use is a space where models are actually not good. So that's the only caveat. On the LLM side, there's no really good open source computer use model. And the latest hotness on Twitter is MCPs. So I just put it there so that this will rank highly on Twitter. So what are challenges? Computer use, we mentioned. User versus agent space. So there's already the idea on a computer of like, there's like the user space in the kernel. I think when agents want to do a lot of things, they can take up a lot of memory, and often you want to use your computer for what you like. So if you're playing a game, you also do not want your model to take up, 10 gigabytes of VRAM. So people still need to figure out whether that is a small personal device for runtime. That's what, George Hotz, who we also had on the podcast, is trying to build with the tiny box. The agent inbox. So today, most use cases are pretty sync. You kind of you got to use the thing and like wait for it to return it to you. There's really no way to like handle handoff between users and agents on long time horizon. So if you want to build something, I would spend time there. And then catastrophic action detection. I got that from Sumit. He's basically like, there should be a threshold of like, if I tell an agent to like go buy me a sweater, and the sweater is a $5,000 Gucci sweater, I should probably know. Versus if it's like, a $70 sweater, maybe that's fine. And today models don't really understand the difference. Multimodality, very quickly. Most multimodal use cases are for input. So nobody's usually doing multimodal output from models, but you might use the live vision on your ChatGPT app where you can like show it a camera, you can talk to it. Those are very successful. Voice is obviously, it's interesting, but like, I don't really see people productizing it as much. My main voice use case is like cursor and super whisper. I just talk to it instead of typing. And then I have a ChatGPT shortcut on my phone. So if I'm driving and I have a question, I talk to it that way. Image generation, most of the labs don't have a good product. Anthropic doesn't have it at all. DALL-E by OpenAI, where is it? Nobody uses it. Gemini image generation, after the whole fiasco about wokeness, I think everybody forgot. Midjourney, still great. Flux is great. It's almost like there's too many good image generation models that like nobody really cares anymore. Like nobody's looking at image generation benchmarks. Like everybody knows that if you want to generate a good image, you're able to today, and then you'll just go try a bunch of them. Music, the music industry is like highly litigious, so they'll just sue you and like try and fight with you. So we did an episode with Suno AI, which is probably like the largest music generation company about 1.5 years ago. Since then, I think they got sued by everybody. So I hope Mikey's doing well. And then on the video side, similar. So video is interesting because there's a lot of copyright stuff there too, but video in itself is a simulation of reality when it's generated. So if you think about the video of an object falling, like that's kind of simulating gravity to see how fast the object is going down, and like once it hits the ground, what happens. So Jan LeCun, one of his big things about language has always been, look, with language you cannot really have a word model, like you need video to like really understand how things move, and like if you can predict the next movement of an object, you really understand all of the physics in the world. So Java and some of these models, VJava, I think it's actually not Java, are examples of that. So this is a Sora video of a podcaster giving a talk at a university. I don't know why he's got the headphones in. It's kind of confusing. But this is, I guess, state-of-the-art-ish video generation today. The LLM OS. So the browser. Everybody, we just had browser-based on our podcast. Operator is maybe like the most visible example of like a given an agent browser access. I think today the main issue is like the web is built for humans, right? Aesthetics. So most websites are not information dense. They're like good looking, which is not always what a model wants. Everything is monetized on ads. So people, the websites don't actually want you to like get to your result as quickly as possible. They just want to show you as many ads as possible. And then it's optimized for spending time. On the other side, the agents care about context usage. So the more information you can put in the context, the better usually it is. They're optimized for quality. So they don't want to spend a lot of time on your website. They just want to get the right thing right away. They're usually like a one-way interface. Like an agent is reading, is going to think, and then do something else, versus like humans are more interactive. So I think today there's a lot of things that we need to rebuild on kind of like the browser and internet usage side. So for example, the thing that I always say is like, when Cloudflare is like, are you human? It's like, am I supposed to be human? Like, can I be a robot? Like that should be okay too. And I think we're going into a world where like, they're also releasing a product soon about good bots and bad bots, where they're basically going to help you figure out whether or not it's a agent that you should welcome or not. Usage rate limits is like a lot of times you might have seen on GitHub, for example, it's like you might hit a rate limit because you're going through too many things that shouldn't happen. And then things like pagination, right? What do we paginate things for? Obviously memory issues a lot of times, but often it's like, hey, look, you probably don't want to get everything thrown at you as a user, but agents are very capable in doing that. So that's another, if you want to work in something that's not models, I think figuring out the future of how information on the web is consumed and acted upon by LLMs is an interesting space. Code interpreting, so we're investors in this company, so I'm biased. But basically, when models want to run code, you definitely do not want the code to run on your machine. I've seen Cursor write code that should not be run on anybody's computer. So what E2B does is basically create a sandbox for your code to run. And now in reinforcement learning, this is even more helpful because you can use this for RL on code. So Hugging Face is trained a model called OpenR1, which uses E2B as kind of like the RL framework for it, so that you can kind of generate code, test it, make sure it works. I had a question about specialized RL models and whether or not we're going to keep using these big ones or have more specialized ones. This is how, if you are, for example, Goldman Sachs, they have a customized query language that they build that only Goldman Sachs uses. So as you might imagine, there's no internet knowledge about it. You can use something like this to fine-tune a RL model on that language specifically. Memory. This is another thing where I see so many open source projects focus on AI memory, and most of them is like summarize a message and put it in a data store. But there's a lot about memory that is non-explicit. You know, it's like if I ask you to go, I don't know, to the movie theater 10 times, and you say no, the memory should not be that the person doesn't like movie theaters. The person probably doesn't like you. You know, it's not about the movie. So those are things that most of the products today don't get. So this is how OpenAI implemented their memory thing. So if you've seen in ChatGPT, there's kind of like memory about you, but what they don't really have is like decay. So information decays, right? Like this month I might be really into, you know, a certain type of music or like a movie or whatnot. It doesn't mean that I forever want to be remembered as like, you know, a big fan of XYZ. So this is another space. If you want to start a company, work at a company, I will probably look at this. I know some of the vector store, like Chroma and folks like that, are obviously like, you know, super interested in this space. So that's also another way that you can kind of get closer to it. Tool use. So yeah, MCP, right? Ranks highly on Twitter. So we mentioned that. MCP is basically like if you have some sort of like runtime or API, how do you structure that in function calling for the model, and then how do you act as the bridge between the two? It's really like you know, if a lot of apps are GPT wrappers, this is like the ultimate wrapper. And then I'm also an investor and on the board of a research lab called AnswerAI, which was started by Jeremy Howard. So if you've heard of FastAI or, you know, now Answer, they came up with this idea of the LLMs.txt. So every website has a robot.txt, which is mostly like, please don't come on my website, stay away. LLMs.txt, the idea is, going back to the browser thing, just give the information in Markdown to the model. Don't ask it to traverse a DOM that has been generated to be good looking for a human. So there's a website called, I believe, llmstxt.cloud or something, that is a list of all websites that now support it and have it. And so that's another interesting idea on the commerce side. So if you're United Airlines, how do you generate LLMs.txt that also has the function definitions for an agent to look for flights, to compare them? And then if you move away from the idea of I'm paying for ads to rank highly on Google, but I'm paying for ads to be chosen by a model, what does that look like? Is it, you know, information completeness, so only if you pay you can show the prices, or is it giving deals, you know, things like that? I think, I don't know if you've seen it today, but basically like Grok started shilling this coin called Grok coin on Solana, and you know, Grok is named Grok, it's in the system prompt, and then people are like, what do you think are good meme coins? And it looks at the meme coins and is like, I like the Grok coin, it's like my name. So I think you're gonna see a lot more adversarial work in this space where people are trying to use names that confuse models. The other example of this is like there's a place I walked by the Engineer Summit, it's a coffee shop in New York, it's called Coffee Near Me. I thought it was a meme at first, but it's actually called Coffee Near Me. So you search Coffee Near Me on Google Maps, obviously you're looking for them. And so we'll see the same thing on the agent side. Other question, are jobs over, right? Like the economy is going to be all AI. I think if you're in school, you know, you're probably like, why am I even doing this and getting in debt to then not have a job? That is not what's happening. So this is the way I've been talking about it with folks. So any company has this kind of like distribution of employees, you know, so you have kind of like people that are not really good at their job. If you look at a company with like 100,000 people, right? A lot of people are not good. Most people are kind of like in the middle, you know, they're doing okay. And then you have people that are great. And then you kind of have this skill gap where, you know, if you think of it in like basketball terms, you have like, the 96 bulls are like at the top of the skill ceiling, and then every other team is like, how far away are they from them? And what AI is allowing now is you basically have a skill floor, which is AI, right? Like to get a job, you need to be at least as smart as like ChatGPT. Like if ChatGPT can answer better than you, it's over. And so what happens is like everybody that is a low performer is basically using these tools to get pushed up the stack, right? So if you're an engineer and you're not a great engineer, you're using Cursor and you're a great engineer, right? So you're moving, the jobs are kind of moving up and up in stack, and the top performers are getting even pushed further up. So you have folks like, I don't know, levels.io, like some people might follow from Twitter. It's like he just builds solo apps, and it's like uses Cursor, and like he makes $1 million revenue on like a app that makes images just because he knows how to move quickly, understands how to marketing and all of that. So we'll see a lot more of that. Like you might imagine the next Mr. Beast is not gonna need 200 people on the production team to run everything, because at the end of the day, he's the person behind the ideas, and like producing the video is actually like pretty, manual after that. And so today, if you look at like most, markets, like the way they're moving is on cutting costs. So how are you using AI to cut costs? That is, Klarna was like, we have a lot less customer support people because we use AI. People are saying, oh, we get a lot more productivity from our engineers because they use Cursor. But really, in the last 10 years, a lot of the companies have not built the muscle of like, could we just accelerate things outside of startups, obviously? Like the large companies are mostly being complacent and like trying to get more efficient. But what AI is now allowing to do is like, you look at a company like Cursor, they're probably now like 130, 140 million of revenue, and they're like 35, 40 people. And GitHub Copilot is like just in the dust, right? Which is like, it's really like a $2.5 trillion company that runs like the most popular code repository. They have all the data, they have all the distribution, and yet they couldn't get there. So you'll see a lot of change in the public markets where getting a premium on growth, it's going to be more and more important. Which before, thanks to 0% interest rates, it was like you could artificially get growth by getting money for cheap, but now that's going to change. And then lastly, I think like you can see every job kind of becoming more of a super job on a long enough horizon. So if you are a salesperson at a large company, you're meeting with a customer and you want to close the deal. Now you got to wait on legal to like get you back the latest draft, which is like always the same document. It just changes a couple things, but like you're a salesperson, so you don't have, you simply cannot do it. And so what's going to happen now, you're basically going to have, AI-enabled tooling for like your core job. So whatever, if you're a software engineer, you're going to use Cursor or whatever, which has AI in it. And then for everything else, you'll leverage services as software. So design, right? Like you shouldn't need for a designer to give you an outline of a very basic like form or like something like that. You can leverage a design agent to help you with that. If you're creating a copy for a new website, you shouldn't wait on marketing to give you some sort of copy. You should have a marketing agent that is already being, trained, so to speak, by the marketing team to give you the copy, and then there's going to be changes, but at least you can start designing with that in mind. So as you're going to think about, what job you want to do in the future, where you want to work, what are the things that you want to do, I will first figure out what are my AI-enabled tooling. You'll be surprised, like still a lot of companies that we talk to, most of the employees that work there are not very sophisticated in AI, even at the large companies. So there's no such thing as like I'm too late, I'm too far behind. And then figure out if you didn't have to rely on other people to enable some of your work, and that work could be soon automated partially by agents. Like what are things that you would do that were not possible before? So say you haven't yet, you have an idea. That's why people say this is like the age of the idea guy. Like say you have an idea for an app, right? It's like now you can easily, if you're a software engineer, you could code it. But before, maybe you didn't know how to do a marketing plan, you didn't know how to do a nice landing page, you didn't know how to do social media marketing. Now, all of those things that are secondaries, you can kind of automate. So yeah, just be ambitious with things that you want to work on. I think that's it. Yeah, I think those are, we work with a lot of startups, and things change really quickly, and we work with a lot of people in the enterprise and what we call the AI Center of Excellence, and yeah, everything is changing, and I think just being here today, I think you're already ahead of a lot of people because they don't spend the time trying to figure out what's going on. So yeah, happy to chat about whatever.
Thank you. Alessio, do you want to, I know we're behind when you started, do you want to take questions here, or do you want to take them over cake over there?
Yeah, if anybody has a question that is like generic that I think people will benefit, or if you have a question that you're curious about, yeah, here you go. We got two right here.
Let me run this mic back to you.
Just about one of the slides. What's that?
How many?
Start hitting back.
Start hitting back. He's like, just go for it. Like a while, or?
A while.
Keep going. I'll wait there. Agent inbox. Yeah, forward like one or two slides. There, this. Yeah.
Okay, yeah.
Yeah, I just had this like bookmarked in my head because I was hoping you could just expand on what you mean by agent inbox, where.
Yeah.
Yeah.
Yeah, it's basically like, when you work with somebody, there are like different levels of urgencies of things. So if you need to make progress on a specific task, like right now, most agents run on a task-by-task basis, but you don't want all of them to necessarily, you don't need all of them to finish at the same time. But today, I have a bunch of personal agents that I run, and each of them is just like in its own thing. And until I respond, it's not going to keep generating. Going back to the nature of these models, it's like they can only generate one token at a time, right? So until you unlock it, it cannot do it. There's really no way with models. Inference is like almost the ultimate like stateless thing, because you can take any pair of like context and model and restart that computation at any time, and the next token is going to work the same way. So there's no way right now for models to take basically an action that they're doing, pause it, and say, okay, I need somebody's help, put that in a separate queue, and then keep working on like the rest of the task. Like the tasks are not always, they don't always need to be sequential, but the models, when they need help, they just stop and wait for help. And so, yeah, figuring out that handoff is something that people haven't quite figured out.
Got it. And do you mean that in the context of like an immediate task, or also tasks that can run over a truly long time frame, like over weeks or months?
Yeah, exactly. And I think sometimes there's like knowledge that you gain, like there's long-term tasks that you don't yet know how to do, like take like tax filings, right? You can start a tax file, but until you get like your insurance coverage document, you cannot go back to it. And like, how does the model then figure out how to restart certain tasks once the conditions are met? One, two.
He was. Oh, I'm sorry.
My question's around plagiarism, because now that there's a very thin line, at least, between human-generated content and AI-generated content, especially for text. I know that OpenAI tried to build a model to identify, and they failed at it. And now I think we're past that, where we can use like a model to differentiate between what is AI-generated and not. We still have a couple of years before we can tell what's AI-generated, at least for images and videos. How do you get about it?
I don't think anybody really cares. I think that's really, like, I think in education, people care, but why? I think it's almost like the plagiarism in academia, it's more of like an ethics question than a technology question. And I think like, it's sometimes an issue, maybe like conferences and things like that, but really like, you can easily tell if somebody doesn't actually know what they wrote in a paper, or like what they're talking about publicly. So to me, it feels like spending, like it's unclear if it's a problem that can really be solved. It's kind of like, because in a large enough N, you can just have the same thing you randomly regenerated twice, So in that case, how do you know if it was just random or if it's actually plagiarism? So I think at a core, it's like a question that like you can't really answer 100% truthfully, And so to me, it's like, might as well go build something else. But
so it possibly doesn't even matter.
That's my thinking. I think some people are like really, I would be pissed if like somebody plagiarized my work and called it as theirs, but that's like a separate problem than like, did the model output something that somebody else had written before? Which I think is more of like going back to the data is like a copyright question. Like, are you trying to make money? Like, if I ask the model, how does Harry Potter start? It should be able to tell me, you know, because if I ask my friend, it would tell me. But if now you're trying to say, this is my book, you know, and it's like Harry Potter, it's like, that's not okay. So again, it's like more of like an ethics and like usage, fair usage question than like a technological question.
Let's see. So, yeah, great talk. I liked the topics. So I had this question about the copyright, because this is something. I mean, I don't. You know, I'm not a legal person or anything, but it kind of scares me because, in theory, like anything that I write is technically copyright. So any web page, anything that anyone writes, they kind of own the copyright to some degree, and then so. Like, we couldn't really train any models if everyone's going to enforce the copyright. So I'm just wondering how you think, like, okay, so you said the walls are coming down. Like, how much do you think this will change things? Like, is it, like, do you see it going as being monetized, like everything will be monetized, or like,
Yeah, I think like, first you need to break it, right? So what Michael Lewis is doing, for example, he's writing this book, which is like why Michael Lewis is like the greatest economist of all time, hoping the models will then train on it and say that he's the greatest. So I think today, we call it like a low signal tokens. So going back to like, you know, nuclear radiation, like steel before and after, like nuclear bombings. Everything before 2021, you can assume is like benign. You know, it was put on the internet and people were not really trying to mess with a model. I think today you're basically to the point where like everything on the internet could be used to poison a model. And we have an episode with a guy called Nicola Scarlini from DeepMind, who's worked on adversarial data for models and things like that. So I think that's why now you're seeing people pay for content, right? And we have some of our companies on the security side also selling data to the model providers. Because now, if I go on Twitter and I script Twitter, which is, you know, what XAI is doing, how many bots do you see on Twitter? Like, a lot of them. And so now, those bots are like financially incentivized to mention topics that might gain them money, you know? And so now it's not a matter of copyright anymore. It's a matter of like, I cannot actually trust that I'm training my model on like high quality data. So I think then the next question is like, well, how should I keep putting my content on the internet, or should I just charge people for it? I think there's really no consensus to it, because there's no way for you to make a deal with OpenAI. You know, there's no like, hey, OpenAI, give me $100 for the training data. You know, but that might change in the future, especially with like the distributed training. So you might say, hey, look, we just need better samples for academic writing about computer science, and we have a bounty for $300 for it. So yeah, it's a good question.
Thanks.
Want to go get cake?
Yeah, sure. I guess we'll wrap it up, Fisher, then. Should we just stop the stream? Thanks, everyone, for coming. That was great. Thank you so much.
Thank you.